Hello and welcome to this next part of coding up the LDSO Twitch version. We will continue in the main function. So last time I had a little bit of problems by setting up the debugger, and there was an error with loading up the images.zip file. And currently I have found out that the reason is that my paths were incorrect. So I went ahead and I checked if there is something wrong with the current file path I'm in. So I have added this statement to find out where is my binary file located, to find out how the relative paths should be written to load up the correct files. And I found out that my launchbot.json was incorrect. I simply had to add an additional parent directory here. So I did that to the files argument, to the vignette argument, to the calibration argument. I think I also adjusted the vocab directory. And lastly, I also adjusted the gamma response curve path. Okay, with that out of the way, I was able to launch the debugger and to actually debug into the program. And that's what I want to show you here. So let's keep it like that. Let's go to the terminal. Let's check if you can see it. No, you cannot. I think this should be okay. Okay, let's clear that. And once again, I make the project as usual. I have a bit of a warning here that is due to the newly added lines of code. So like these ones here, it's not programmed very nicely. So we will get rid of that anyway. So let's just keep it like that. So it was compiled and now I can rerun it. So in the beginning I have the output current path is home AKP and then vslams. And from this directory I can move to the next directories. Okay, let's get rid of that and let's try out the debugger, because this is actually not where the debugger is starting, I think. So let's maybe comment it in again. Let's save that and let's go to the debug workspace and let us start the debugger here. There's actually a difference if I started here or from the status bar below. So I will start it from here. Okay, it's not running the way I wanted it to run. So it's for the demonstration. Has a bit of a problem, it seems. Okay, no, it's actually running fine. But now the output is in this terminal here for the CPP debugger. And the program has now finished because I have no breakpoints set for this debugger at the moment. And here you can see that the current path is, let me check if you can see it, yes. The current path is home, AKP, and then vslams, and then LDSO Twitch, and then examples, which means that I have to go into the parent directory, into LDSO Twitch, then into the parent directory again, and then once again, and from that I can go into the vslam datasets, as you can see here. And this is why I had to adjust this path, and I had to try out several things, and that's why it was not possible to show it on camera, because I had to get my head around that first. Okay, so far about the explanation. Let us now start it again, and let's create a breakpoint here. For example, maybe here somewhere, before parsing the arguments. And let's restart the debugger. And let me see if it starts. Somehow it's not starting. Don't know what is going wrong now. Okay, let me quickly try to find out what the reason is. I thought I am prepared for that, but it seems that I have missed something. So by the way, here also in the make project file, I have also changed the build type from release to debug, so that I can just make the project as usual from the command line, like here. Now let's go to the debug layout again. Let's make sure this is selected. Maybe let's try clicking on the status bar here. Now it's building the program. Okay, and now it is running. Okay, I still need to really understand how Visual Studio Code is working, to be honest. But yeah, at least now it works. It started the debugger. It stopped at the for loop for parsing the arguments. And now I can, as usual, just step through the instructions. For example, I can step over and I can step into. Doesn't make sense here, but I can now step into the reader, for example. And I can see how the constructor is called from the image folder reader. I can get an overview of what kind of variables I have. Like, for example, the dataset type, path, calib file, and so on and so forth. They are not defined. So I can just step into that. And now I can see that now the arguments are showing up here, which are the correct ones. That's another thing you need to be aware of, that the path and the calibration file, they should come, these arguments should come from your actual launch.json file. Sometimes that's also mixed up. Sometimes, depending on what you click here in the IDE, it just takes your variables from this main file. Yeah, they are now identical because I've tried something. Yeah, this needs to be double checked. Okay, but this is now very helpful for us, so we can see that we have the actual variable overview here, the variable explorer, I would say. We could say we want to look into the class that we are currently inspecting. In this case, it's the dataset reader. And the dataset reader, if I'm not mistaken, should have variables or fields for the undistorter. There's an undistort here. Yes, and in the constructor of the image folder reader, it is defined like that. So when the constructor is called, the undistort variable is initialized. It will get the undistorter for a specific calibration file in which we can define what kind of camera model do we have. Do we have a pinhole camera model, a field of view model, I don't know, a radial tangential camera model, and so on and so forth. And this way the dataset reader will be initialized, and we can use it in the main function. If we go to the main here, so here in this main file, we'll create it at some point. Here the reader is created, various things are set, the global calibration and the photometric gamma is being extracted or returned, and the usual stuff with loading the images and so on and so forth is starting. There's one thing I want to change still here. That is, I want to really now get this init Google logging running. And I have looked it up. It's working like this. So you have the namespace Google, and in the Google namespace you have the command init Google logging. But there's one argument that needs to be provided, and this is the arg values from your main function. And this should be the necessary command line. And it should work, I think. Maybe we need... I think we should be... Yeah, we need to dereference that. Which I think should provide the program name. Yeah, something like that. Let's now rebuild that. Okay, build is finished. Now we can start it. And it stopped here. You can play it until the breakpoint. And in the terminal, there is only the output for the current path, which we can get rid of because we do not need it anymore. And there is no error showing up that the init Google logging is not, not happening here. You can play it. Yeah, there was this error before, but now it's gone because we have this Google logging initialized now. All right, let's stop it and let's get rid of this path output and let's save it. Okay, let's quickly recap what we have so far and where we want to continue now. So if we take a look at the main file here, we can see that still, there's this to do I can delete now, that we have almost no to-dos in the beginning, and we are now reading the dataset. We are setting the global calibration, we are getting the photometric gamma, so the geometric and the photometric calibration, both of them are fine. We are setting several settings to reorder the images that we can load. For example, if we want to play them in reverse, which we do not do in this case, but we could. Next, we are loading the orb vocabulary for, this is usually used for the loop closure. That is, we have several images which might show the same place. So a landmark that is observed twice or for a third time. And this ORB vocabulary will help us to get those loop closure candidates, which we can then use to correct the whole camera trajectory. This is very useful. We need this vocabulary for this kind of feature. And this is a custom check added last time, where we can print out how many words we have in the vocabulary. And in this case, there are almost 1 million words in this vocabulary. So this vocabulary that we load here using the voc path, this will contain already many words for us, which will then be tried to be found during analyzing the data set. Okay, and after that we have a big to-do, which has something to do with something that is called a full system. And a full system is, in my view, the really important part of this whole Visual Slam that we are creating here. The full system will take up an argument, which is this vocabulary, which we have defined above. So we can create a full system with only having this vocabulary loaded, which we have at this point. And with this full system, we have access to the whole, to every important functionality of our Visual Slam system. So everything that we have done up to this point is only a preparation. It's really just the necessary stuff. But the full system is where we could say where the fun begins. But at the same time, the full system is the most complex kind of component in our whole system, in our whole Visual Slam. And that's why I think, or well, I thought, does it really make sense to start coding up the full system in this part, or should we just code up the individual components that we need for the full system? So there are two ways how we could proceed from here, but I have decided that we should actually tackle the full system in this part, maybe only the header file, because with the full system we exactly know what we need. And we can then, similarly to how we have created the int main function here, we could then go ahead and implement everything that we need to make the full system functional. Okay, so the decision I made here is that I want to code up with you the full system in this part today. The CC file, so the implementation of the full system, I'm not talking about the header file, but the full system implementation has about 2000 lines of code. The greatest or the largest file that we have loaded or that we have implemented up to this point was the undistorter. The undistorter had about, I think, 800 lines of code or something. Let me quickly check. So let's go to the undistort.cc. It's in the source files, internal, no front end, and then undistort. So let's take a look. Okay, there was a little bit more. So about 1500 lines of code. And I think this was about 6 hours, 2 video parts together. So yeah, it will take a long time, I think. But nevertheless, it is really the core of the Visual Slam. So we need to implement it, and at some point we need to start with it. So why not now? I think we have enough experience with the previous functionality of loading up the images. We know what a minimal image is. We know what an image and exposure is. We know what kind of settings we have. We know what the undistorter consists of, how we load images using OpenCV. So we can use this fundamentals, this basic knowledge, and now build upon that by really going into the meat, into the core functionality of the Visual SLAM. Okay, without further ado, let's now go back to the main file. Let's save that. And let us now create the FullSystem.header file. This will be a file that is present in the directory frontend, so similar to the undistort. So here in the include directory, then frontend, and then here we will have an FullSystem.header file. So let's create that by clicking on new file, and let's now write FullSystem.h. Okay, now we have the FullSystem.h, and now let's code up the header file, even though there will be a lot of things that we do not have yet. But as usual, we will create a to-do, and it will maybe get a little bit frustrating to know that, oh, we do not have that, and we do not have that, we cannot test it, and so on and so forth. But it's a process. Okay, so I hope you can you will bear with me, and you will still be happy to watch it or code it up yourself, of course. So let's just start. Okay, we start with a pragma once, as usual. And I'm having trouble to type once again, but we will still be able to code it if not defined. LDSO Twitch, and then we have the full system header file. If it's not defined, we will define it like this, and in the end we'll have an end if. And let's, for clarity, also add this comment. Okay, so these are our header guards. And yeah, let's start with the usual stuff. So first we have the standard libraries or standard template libraries. Does not really have to be the standard template libraries. It can be like any library that we have. So in general, we have 4 of them. We will add the library with include, and then we will add dequeue. So we will work with lists. We will have a lot of data that we need to store somewhere. And this is usually stored in lists, and those lists need to be manipulated. So just think about the camera trajectory. So for every image, we'll have a specific camera pose. So that's a position and that orientation. And this will be stored somewhere in a list for every image that we have. And we need to somehow manipulate this list, and the dequeue library is one of, has functionality to do parts of that. Then, as I just mentioned, we will have a memory. So we add memory here as well. Then next we will have another important thing that we have to add. That's a mutex. And the mutex is useful if we work with multi-threading. So we have one big issue, and that is that we have a lot of data. So if you take a look at the data sets again, for example, sequence 45 again. So these are our images. and these images need to be stored somewhere, and we will have algorithms that will take the image and will analyze that. So usually we want to find specific 2D feature points in those images, and this will take some time. So finding those images, those features in the images, that will take up some time. Then we want to do something with the 2D landmarks. We want to somehow calculate what kind of camera movement do we have in between two frames, for example. So in between those two frames, which do not change a lot, but here, in between those two frames, there is some kind of camera motion going on. We want to calculate that, and given the 2D feature locations in the images and the camera motion, we then want to calculate the 3D position of the 2D feature positions. And this whole computational algorithms that we need to use here, they will take up some time. And if we do all of that in one thread, so in just one single function, in the main function, for example, then this would not be as efficient as it could be. So we would need to wait until the features are found, until the camera motion is calculated, and until the map is created, and then we can go on and take the next image, like this one, for example, and the next, and the next, and the next. To speed up things and to make it more efficient, and also to be able to look at the results in a 3D viewer, you would need to move specific tasks onto separate threads. And the problem with that is that the different threads will need to access the same data. For example, if we want to compute, for example, the camera motion between two images, like these two, for example, we compute the camera motion and we store it in the FullSystem. For the next frame, for the subsequent frames, we maybe need to access this camera motion to say I want to, for example, have a constant velocity motion model that will just take my previous calculations and just use them to predict the next camera motion, for example. So this is one axis. The other axis would be the 3D viewer. The 3D viewer also needs to have access to the camera motion because we may want to display the camera trajectory in this 3D viewer. So there we have a conflict. Two parts from the algorithm, they want to access the same data. And now I've talked a lot about it, but the mutex is actually useful if we want to say, okay, now I want to lock this access of the data, and I just want the 3D viewer to access the data. And then after this is done, I can unlock this data, and for example, the other process that was using this camera motion for prediction, for example, could then access it by also locking this data set for this specific task and then unlocking it again. Okay, and if we have this mutex and I have talked about the threads, let's also include the thread library. Okay, so these are the standard libraries that we need. And now let's continue with the own data types that we have. And now there will be a lot that we do not have yet. For example, one of them is the frame.h file. So we will have a data type for a specific frame. And this is not necessarily like an image. For example, like this image. This term can be used interchangeably, but the frame could contain additional information. For example, I think it is the case here that a frame contains, for example, every feature point that is associated to one specific image like that. Or it could also, I think it could also contain the actual pose of this frame, like the camera motion. And there are other things that need to be stored somewhere, and they are stored in this frame data type, which we do not have yet. Then we have other data types like a point, and we will also have another include. Okay, I somehow deleted it. Okay, let's rewrite this point, and now we also need a feature. So the feature would be, for example, this specific neighborhood of pixels that tells me something about the image. A corner usually. Then we have a camera, which is also very important because we have cameras. We are actually using a camera in reality, and somehow we need to have a visual representation of this camera in the computer. Then we have one thing that we already know, the image and exposure .header file, so this should be known. Then we have the DSO viewer .header file, which is our 3D viewer. Then we have another include for our map.h. So we also need to represent the 3D point cloud, the 3D map, and this will be stored in map.header file. And we will have new types. For example, here we have a feature detector .header file, and we will also have a feature matcher .header file. And this is something we usually do not have in the LDSO, or let's say in the DSO. So when we are implementing these kinds of visual slams, which are also called direct visual slams, we do not have a feature matchers usually. We might have feature detected features in the images, but we do not want to match them usually because we have other. There's a different methodology. We do not rely on the feature matching, but we are relying on matching image intensities or pixel intensities usually. But this feature matcher is, in this case, I think necessary for the loop closure, which is one of the new additions for the LDSO. And therefore we need a feature matcher to match features and loop closure candidates with each other. Okay, and next we have another include, which is the pixel selector 2.h. Okay, and then we have two helper includes as well, which are also from the internal file structure. So the first one is really coming from the internal directory. So it will be created in this internal folder here, and it will be called index thread reduce.h, which is something multi-threading specific again. And then we have another include, which is the loop closing header file. So there will be a specific loop closer which we can use in our implementation, and this will need to be prepared as well. Okay. So let's name that as well here. Our custom let's maybe write our custom data structures. Well, let's not use custom but own data structures. Somehow it's not recognizing the image in exposure, which is weird. It should recognize that. It was able to recognize it a minute ago. Maybe we need to just continue and then Visual Studio Code will find the file. Okay, next we will define the namespaces we use. So for one, we will use namespace std. We will also use the namespace LDSO. And we will also use the namespace LDSO internal. And I cannot forget the semicolon. Good. Here we have another variable that is defined globally, which is a constant integer and is named max active frames, which is equal to 100. I have no idea why this is not a setting in the settings.header file. So I would usually expect it to be somewhere here, named setting underscore maximum number of active frames. But okay, I will keep it like that. These things can be changed later if we want to. Okay, next we want to define our new classes. And they will live in a namespace, which is LDSO, just like the other ones. And we will open it and then we will start defining our stuff here. So first of all, we will have a class that is the course tracker. This is an important one because the course tracker is usually the very first thing that will provide us with a relative camera motion between two frames. It will be used together with another class, which is the course initializer. So I think the initializer will be called first. It will try to initialize from, for example, 8 images to get an initial camera motion from that and an initial map. And then I think this solution will get handed over to the course tracker, which will then continue to track the remaining images. Then we have our class image and exposure. So this is just a forward declaration of the classes so that they are known within this file. Because we already have the image and exposure class, this will be loaded from the header file here. And therefore it will be available for us. And then there's another class, which is the course distance map. And then there is another namespace defined, which is the internal namespace. And in the internal namespace, we will have a class called point frame residual. Then we have another class, which is the imager point. So we will have stuff like let's say we will have imager active. There will also be, I think, out of bounds, and so on and so forth. Kinds of points. So if we have an image and we want to track specific points in the images, specific pixels, they will in the beginning be some kind of, you could maybe say a hypothesis, so a hypothetical point, which we then, if we trust it, can make an active point. And we can create a 3D point out of that. But this point can over time also get, for example, occluded, or the camera is moving very fast and the feature point is not seen anymore. This will then be out of bounds. So we somehow need to give some sort of meaning to the 2D feature points. And one of this meaning is that we say we have imager points, for example. Then we have another class called the energy functional. And we will have a struct called imager point temporary residual. Okay, so these are our forward declarations for classes that we have, basically the data types we will use. And you can see that there's already a lot of them. So of course we will have our images. The images will have associated camera calibration, like exposure and vignette and gamma and so on and so forth. We have an initializer, which will make the beginning. Then we have a tracker, which will then take over and do the rest of processing the images. And for every image, or for the whole scene, we will have a distance map. We'll have points and frames and residuals, so some kind of error terms. We need to store the points. We have energy functions that we want to minimize. And we also have some kind of temporary residuals that we need to store somewhere. Okay, with that out of the way, we now want to define the full system. Let's create a short description what this is. So the full system is the top level interface of DSO system. Call add active frame. I will add the parentheses here to track an image. So here's very important information for us. As I told you a lot of times, I think the full system is really like the core component of our Visual SLAM system. And there is also the function add active frame, which I will show you quickly in the main function. So here, when we start with creating the full system and so on and so forth, we'll at some point define a separate thread. And in this thread, after we have loaded the images and initialized the timer, the stopwatch, then we have, we can initialize the images. But at some point, if we do not want to skip the current frame, we'll call FullSystem add active frame with the current image that we have created or we have loaded. So that's an image and exposure. And we pass this image with a specific index or number into the full system by calling add active frame. So this add active frame is our interface from the main function into the logic of the full system. So keep that in mind, please, that this is something that we will probably face when we are starting to pass the images onto the full system. Okay. Okay, let's define this full system now. So it is a class, of course, which is called FullSystem. And what is inside this class? First of all, we will have a public scope, and we will at some point also have a private scope, as is the case with most of the classes we will use. But this will be here a couple of times. I think maybe only twice. So let's copy that because we will have the same. So this, let's maybe comment this. So these are the methods we'll use, and these are the fields or attributes, variables, and so on and so forth. And we will also have these areas later for the individual threads. So we will have, for example, a tracking thread. We'll have a mapping thread. We will also have a loop closure thread. And I think there's another. So of course we will have a GUI, so a graphical user interface thread. And yeah, we need to manage them somehow. And therefore we will here also have public and private scopes, but that's not relevant at the moment. Okay, and then we want to close this class definition with semicolon. And yeah, we can now start to add the definitions for the individual methods and so on and so forth. So in the beginning, in the public scope, we want to add a macro, which is the eigen make aligned operator new macro, which will provide an optimization for us. And I'm somehow missing my IntelliSense here. It would be helpful if I would be able to use it. Maybe this is because those files cannot be found. So let me add the first to do in this part. So actually there's everything we want to do here, but we will have the image and exposure. So I would like to somehow separate that. I will do that by breaking up the multi-line to do here. Okay, unfortunately it's still not finding this. numtypes.h. Okay, now it has found it somehow. I don't understand it, to be honest. Okay. All right. Okay, after we have defined this eigen make aligned operator new macro, which will speed up our eigen library, we will add the constructor. So the full system will take in a shared pointer of type orb vocabulary, and the argument is called voc. So with only this argument we can create the full system. And because we will probably use new commands, we also need to define a destructor, which will then clean up the memory for us. So this is the constructor, and this is the destructor. Okay, after that we will have, and it will be a public method, of course, the very important one. Let's comment that. A method which adds a new frame and creates point and residual structs for us. So we'll have a void add active frame, which takes in an image and exposure pointer to the image and an integer for the ID. Oh, we have a chat message. Hello there. Nice to have you here. I hope you will enjoy the video. Feel free to ask something if you have questions. Thank you for watching. Rahomo. Okay, then we have another method which will block the tracking until the mapping is finished, and it will return when the mapping is finished. So this method will be called, it will be a void method and called block until mapping is finished. So why do we need that? We need that because the mapping, so creating the 3D point cloud from the image data, this might take some time. And if we, for example, want to stop the Visual SLAM system, we first need to wait until this mapping is finished so that we can, for example, display it. And therefore we need this method. No questions. I do state estimation for drones, so I'm excited to see the stream. Oh, that's nice. Maybe you can tell us about this. You can tell us more about that. So a state estimation for drones, so you probably need to work with the pose information of the drone. Maybe you have special Euclidean groups and special orthogonal groups, Lie algebra, and so on and so forth. This is stuff that we need to implement in this LDSO as well. But maybe you can just write a little bit about that. Are you using cameras, or are you using LiDAR, or are you using, I don't know, other kinds of sensors, radar? I would be interested to know more about that. But of course, you can also enjoy just listening to the stream. Okay, next we will have a method that will do the optimization for us. So optimization is a big, it is a big probably, but it will also be an important part, because we will define energy functions and error terms that need to be optimized. And this optimizer, there will be several of those optimizers here in this code, and they will usually be implemented in, for example, this method float optimize, and they will take an integer for the mnum opt its, which I think stands for the minimum number of optimization iterations, but I'm not sure. We will see when we have implemented that. Let's add a bigger comment here. So here we want to optimize the system by calling another function which is called solve system. Then we have the parameters. So we will have a param mnum opt its. Number of iterations will be changed if active frames are less than 4. And there's a return value, return average energy. So this float that is returned here is the average energy. Whatever that is, we will look at that when we implement that. Okay, yep, I've worked on various platforms. We use EO and depth cameras. Is EO an event camera. I'm not sure, maybe you can explain it. And depth cameras. LiDAR, IMU, GPS, okay, MSCKF, and Vince Mono based backends. Nice! So you usually use the full stack, which is amazing. Yeah, feel free to maybe link your work somewhere. I don't know if I can maybe later look up your username and find something, but feel free to just post, I don't know, your GitHub link or something, if you want to, of course. Thank you for explaining it. So here we want to set the gamma function into what is called the camera calip Hessian. So we'll have a lot of these Hessians here. We'll have, I think, a frame Hessian, we'll have a point Hessian, a calip Hessian, which, as far as I understand, they just collect the whole information about a specific kind of entity, and we need to access it. Thank you. It's all in work repos, so nothing to share. Yeah, I know that. Yeah. I also have work-related repos, and yeah, I cannot share them as well, but I'm also looking into this kind of stuff. But it's nice to have someone like-minded here, and yeah, also working with this in this kind of area. Okay, this method will be called, it will be a void called set gamma function, and we'll take in a float array or float pointer for the binf. Ah yeah, I forgot the param here, which is not very surprising, that the parameter for this function is the b inverse. And I'm not sure what the binf is, maybe the brightness inverse. I would usually expect the gamma to be a ginf, for example, because the gamma we have loaded it in the, I think it was in the, was it in the dataset reader or in the undistort? I'm not sure at the moment. We have definitely used it in the undistort. Let's maybe quickly look it up in the undistort header file. And it's of course in the photometric undistorter. So here, for example, there's a get G, which is the gamma response. And here we have a B. As I said, I'm not sure what this is at the moment, but we will see it. Then we have another method, which, let's add a comment, which will shut down the system. It is also called when we are resetting the system. And it will stop the loop closing thread if the loop closing is enabled, if it is enabled. So later you will see that in the graphical user interface there will also be a button which you can press, which reads reset, and this way we can reset the whole system, and this will call the shutdown method. So let's write it, void shutdown, like this. I think we can also see it in the main function. If we search for shutdown, No, it's not here, but we will have a reset somewhere. So we can set a setting by pressing the graphical user interface, which will set this setting full reset requested. And when the next time this loop gets executed, various things are checked. And if this is requested, then we will set, then we will reset the system, which means that we just reinitialize the full system here with the same command that we have used above. And yeah, we also reset the viewer. But we are not really calling the shutdown method, which will then be called from somewhere else in this case. Next, we want to save the information. So we want to save all information into a binary file. And if we want to save something, we usually also want to load that. So we want to load all information from a binary file. And the method is returning a bool, and it's called save all. And it takes a constant string with a reference to the file name. And similar to that, we'll have a method called load all with the same argument. And now we have talked about the state estimation, so we need some kind of states. We need to define state variables. But this is actually not about the state of the moving camera, but it is about the state of this full system. So we'll have a few bools. So bool is lost, which is false in the beginning. So the full system can be lost at some point. When? For example, if we move the camera very fast, or if we have outages in the image stream, just basically something happens that is not good for our algorithm, and then the whole system is lost. We'll also have a bool which is called init failed, which is also false in the beginning. Maybe let's add some comments here. So if system is lost, note that DSO cannot recover from lost. So this is actually a very bad thing about the LDSO and the predecessor, the DSO. Once they are lost, they will remain lost. Yeah. If the initialization fails, or if init failed is true, then we have an information about the initialization failed. Next we have also a bool which tells us if the system is initialized. So here similarly initialized. And we have a bool which says linearize operation, which is true. And I forgot the semicolon. And this explanation here is this is something. This is something controls if the optimization runs in a single thread. Maybe there's missing a that. This is something that controls if the optimization runs in a single thread. But why it is called linearize operation ... question mark. So this is the original comment. I totally agree. So why do they call it linearize operation? I have no idea. Probably, I don't know. I will not try to interpret it. There are specific things or certain things in this implementation which I think I will never understand. But the goal of this stream is, of course, to understand that. And even though some stuff is cryptic, we might be able to understand it once we are really working with it by implementing it in this stream. Okay, next we will have another method which will return a shared pointer to a course distance map and will be called getDistanceMap. And here, this is defined inline, so we return the course distance map, which we need to define at some point. I think it will be defined later. So this is a member variable which will hold this kind of data type here, course distance map, which will have something to do with the point cloud. Okay, next we also return a vector of type shared pointer, which is of type frame, which is called getActiveFrames. And this will, as you might already know, return the frames. But here we will have something I have discussed in the beginning. That is, if we want to access specific data structures from different threads, we need this mutex. So we can write unique lock of type mutex, and we name it LCK for lock, and we lock a specific mutex which we need to define, which is the frames mutex. And the nice thing about this unique lock is you do not need to lock it and then unlock it, but it will be only active. So this lock will be only active in this scope. So you basically only write one line and it will handle everything for you. Okay, next we will have another method of type void, which is called refresh GUI. So that's the graphical user interface. And here we check if we have a viewer. So if viewer, then we say viewer and then refresh all. So if you have a 3D viewer, you of course want to display something in the 3D viewer. But you also need to have a way to update the display somehow. And I think this will be this refresh GUI command, which will be called from time to time. But of course, as with everything, we will see that. Okay, in this private scope, we will write a comment that we will begin main pipeline functions. Note, maybe a colon here, track and trace is different. Let's make a full stop here and let's write track is used in every frame to estimate its pose. And trace is used to record the immature point tracking status. So you will see that when we continue implementing the full system, we'll have one specific component which will track. So the track is related to not the feature points, but actually the camera pose. So if we have multiple images, like let's take again a look at this data set here. So if we have this TUM mono dataset, if we have every image here, for every image pair we want to estimate the camera pose, and this is called, this is what the tracking is used for. And we also have this tracing, which is then related to the feature points. So we have the points in the images. So for example here we have the points on, for example, on this structure in the middle, on the corners for example, and now we want to update the status given we have new images. For example, this corner on the left hand side will at some point, maybe not here but somewhere later, like here for example, move out of the image and will then have the status out of bounds. Whereas in the beginning it was maybe immature, and then it got active, and then out of bounds, and so on and so forth. So we need to keep track of specific states in our algorithm. Next, we will define a method which marginalizes a frame. That means it drops or marginalizes points and residuals. The residuals will be dropped, but we still have this frame in the memory. So once again, if we have the images, we want to decide, when we go through each image, we want to decide what do we want to keep and what can we safely throw away. So at some point, it does not make sense to keep information about this this object in the memory, because if we move away from that pretty far, then why do we need to keep track of this object specific things if we are now moving, for example, a kilometer further away? There are, of course, situations where you should store that and keep track of that, but usually at some point we want to just, let's say, throw away old information, and that is what marginalization from very high perspective means at this point. What it means mathematically is a whole different story. And therefore we have a method which returns void, which is called marginalize frame, and it will take in a shared pointer of type frame, and it is called frame. It's a reference to a frame. Okay, next we will have another comment which describes the next method, and the next method tracks a new frame, and estimates the pose and affine light parameters. So the affine light parameters will be this magical A and B parameters, where one of them means the contrast and the other one means the brightness of the image. And the pose is usually an SE3 pose, which stands for Special Euclidean Group. Say it's a group, and it's abbreviated by SE3. It's a so-called Lie group, and this is what we need here. Now there's a param in this function, which is called FH, which stands for frame Hessian, and this is a new frame, and this will return a 4D vector which has some tracking status information. used to judge if we need a new keyframe. It's maybe not right, a new keyframe, but a keyframe. So, hello Anton, greetings. Thank you for watching. I hope you have fun watching. Yeah, what is a keyframe? I wanted to discuss what is a keyframe. So we have our images, which you can see here. So these are our images, we analyze those images, and a keyframe is a specific one from these keyframes, which has, let's say, I'm trying to find the right explanation, which has high information value, I would say. So for example, we could say that even though we have multiple frames here, only one of them is important for us to remember something. So if we want to remember this big object here, we can also just store this keyframe, and we basically can forget about the other keyframes, which are of course useful or necessary to calculate the camera motion. But when we talk about the image content, only one of those images is sufficient. Okay, what does this program do? We are implementing the direct sparse odometry with loop closure, and the program takes in this image sequence here, which you can see here, which is from the TUM Mono visual odometry dataset, and it will analyze the images to try to reconstruct the camera motion and the 3D point cloud of the what the images are showing basically. It's a Visual SLAM program, and Visual SLAM stands for Visual Simultaneous Localization and Mapping. So it takes those images and uses those images to localize the camera and create a 3D map out of that. It's the Visual SLAM system. And we are implementing one specific open source variant, which is available on the internet, and it is called the LDSO, the direct sparse odometry with loop closure. Yeah, and we are just trying to understand how it's working, and so on and so forth. Do you have any sensors that give you scale? No, there are no sensors that give us scale. That's actually one of the issues. We are talking about a monocular Visual SLAM system here. That is, we can only reconstruct the camera motion and the 3D point cloud up to an unknown scale. If you want to have scale, and you probably know it, Rahomo, you can use a stereo camera, for example. Okay, so let's continue here. Okay, we want to return a 4 vector, so we need to define a return type, vec4, track new course, and it takes in a shared pointer, which is a frame hashing again. Yeah, nice. Yeah, I totally agree. It's nice to have an algorithm that only takes in images and spits out everything we need. Besides scale, we usually also need the correct scale, but there are ways to solve that. But it works only with images, and we can create a 3D reconstruction of our scene. In my view, that's amazing. It's magic, and I want to understand this magic, and that's why I do this stream, and I hope it will also be enjoyable for you. I don't know, maybe it's also boring. Yeah, feel free to give me feedback. The goal of this stream is only to to look into the code and try to work with it and try to understand how the authors of LDSO did it. Yep, I love it. Thanks. Great to know. Okay. For vector. Okay. I don't want to mix up things here, so now we have this track method that we discussed here. So we have this track, and we also need this trace method, which will be added here. So we trace imager points into new frames, maybe keyframe or not keyframe. Let's create this dash here, or not keyframe, to update the imager points, I think, imager point status. Let's write in a new line to update the imager point status. Full stop, and then FH's pose should be estimated, otherwise trace does not make sense. Okay, one just needs to understand this comment. So FH is the frame Hessian. The pose of such a frame Hessian should be estimated. Okay, I think that's clear. But otherwise, trace does not make sense. Yeah, of course, the pose needs to be estimated. Otherwise, the whole algorithm does not make sense. Yeah, and we have a param here, which is FH. Okay, let's write the method. So it is of return type void, and it's called trace new course, and it takes in a shared pointer of type frame Hessian with FH again. Okay, next we need to activate point and turn the imager into real points and insert residuals into backend. And called in making keyframes. Okay, so let's review that. We have activate point. This will turn our imager points into what are called real points, whatever that is, real points. So in the beginning we have in the image selected several of those corners and interest points, and these are flagged as imager, and then we will update the status, turn them into real points. That is what this method here will do. And we will insert residuals. So residuals are energy terms, basically like an error we can calculate, into what is called the backend. In a Visual SLAM, we usually have a front end and a back end. The front end will do all the preparation stuff, like, I don't know, finding features in the images, feature points, interest points, doing initial calculations, and then the backend will correct the whole mess that was screwed up in the front end, I would say, to keep it very informal at this point. Okay, called and making frames, and this is called, will return a void, and is called activate points, and then there's a capital MT, and this MT, as far as I know, stands for multi-threading. So there are specific methods which are optimized for multi-threading, and they will usually have this MT suffix here. And now we have something related to that. We will have a reductor for activating points. We'll call optimize imager point in a multi-thread way. Okay, so the method is defined like this. It will return a void. It will be called the same, activate points, empty. But this time we add another suffix, which is called reductor. And the argument list is a bit more complicated. So first of all, it takes in a standard vector of type shared pointer, of type point Hessian, and this will be a pointer to the optimized, probably to the optimized point Hessians. So this will be a list, as the name already suggests. Then we will have another list. Let's write in a new line. It's also a standard vector of type shared pointer, of type imager point, and this will also be a pointer to a variable called toOptimize. toOptimize. And then we have some additional information like an integer min, integer max, a vec10, pointer to stats, and an int tid. Okay, let me grab a drink. Okay. So we will have quite a few times, we will see that we have methods that end with empty, which stands for multithreading, and we have an associated reductor. I'm not sure what this reductor is used for, but it's something seemingly specific to multithreading. Okay, then we will have this method that is mentioned here in this comment. But let's first add an explanation to that. So we want to optimize an imager point if the I depth, which probably stands for inverse depth, is good. Then we create a map point from this imager point. Okay, so we get this imager point, and then we check for this one point, we check the inverse depth, if this is good. So usually it's optimized, the inverse depth. If this is good, then we create a map point. So we convert this imager point into something that we really want to now, want to first display in the viewer, and secondly use for the subsequent images that we process. For example, by projecting it into the new images and reprojecting it and back projecting it and doing some calculations with that. Okay, this method will have params. The first one is called point, and this is the imager point must have a host feature. Then we have a second parameter, which is called min OBS, minimal good residual required if the imager points good residual is less than if the imager points good residual is less than, it will be marked as an outlier. Okay, I think there's something wrong with the grammar here. Okay, minimal good residual required. Maybe let's make a full stop here. Let's put it into a new line. If the imager points good residual is less than it. Oh. If the imager points good residual is less than it, we marked as an outlier. I do not understand it. Probably we need an it here. Less than, I don't know what this means. If the imager points good residual is less than it. What? Is less than, maybe that minimal good residual. Ah, okay. If the imager points good residual is less than maybe this min OBS. I don't know. I'm just guessing here. It will be marked as an outlier. Okay. I think this makes sense, but we will see that once we get to the implementation. Okay, then we have another param, which is marked as in residuals. The residual of this imager point over other frames. So the size should be, the size should be frames.size -1. Okay, I think this makes sense. So we have n frames, which is frames.size. And we have one specific imager point. For which we have residuals for the other frames, and this should be then n-1. Yeah, something like that. Not completely sure, to be honest. Yeah. But it somehow makes sense. Then we have the return parameter. Return null pointer if not converged, or a newly created point hashing if converged. Okay, so this method that we will create here will return a null pointer if it is not converged, and if it is converged, then it will create a newly created point hashing. Okay, so we have a shared pointer as a return type of type point hashing, and this method is called optimize imager point, and it takes in a shared pointer from the internal namespace, the type imager point, called point. Let's maybe reorganize that. Okay, so the return type is shared pointer point hash, and then the name of the method is optimize imager point. The first argument is a shared pointer to an imager point, which is called point. Then we have an integer for min OBS. And then we have a shared pointer of type imager point temporary residual. No, wrong. There's a vector of type shared pointer of type imager point temporary residual. Then we have a reference to the residuals. Okay, this should be correct. All right. Next we have another comment. That is that now we want to add new imager points and their residuals if loop closing is enabled. Use corner detection. Otherwise, use DSO's key point selection method. Maybe I will look that up quickly, show you that in the paper. DSO tum. Okay, something just happened. I hope I'm still streaming. It seems like that. I think I had a short hiccup from my internet provider. Okay, so here, maybe let me quickly move that. Okay, so here you have the direct sparse odometry. This is the video. You can see a short demonstration how this works. So this is the predecessor of the LDSO. You're still streaming. Thank you for the info. And here you can see on the left-hand side, by the way, the keyframes that are stored here. So they look like they are not very fluent, but they are actually only like a keyframe, as the name already suggests. And in this DSO paper, which we can open here, there is a lot of specific stuff that we will use in the implementation. That is, for example, if you take a look at the calibration, we have talked about that. Point selection, I'm looking for the point selection or point management, yeah, like this, for example. So let's take a look at that here. So if you take a look at the images, in the top row you will see the original images, and on the bottom you will see what kind of feature points the DSO is selecting here. So if you have an image like this one, where you have a lot of detail, it will try to select points across the whole image. But then you have textureless areas, like this wall and this floor, where it usually does not select feature points. And yeah, you have these examples here, where you can see that it usually tries to create a lot of points across the whole image. But when there are textureless areas, it will concentrate on regions of the image that contain helpful information, like those lines, for example, or those edges. So this is the candidate selection as it's written in the paper, or candidate point selection, and it's explained here. But of course we want to take a look into the code and not read this here, even though the paper is interesting. Okay, add new image points and the residuals, and we have two parameters, param new frame, and we have a param GT depth, which I would think that GT depth is ground truth depth, but I don't know where they should get that from, so maybe it's something different. Okay, this will return void, and it's called make new traces, and the argument is shared pointer of type frame hashing, and it's called new frame. Then there's a float pointer to ground truth or GT depth. I don't know if it's ground truth. Okay, so this will add new imager points and the residuals. This make new traces method. Next we have a method which will initialize from the course initializer. We'll have a parameter param new frame. Return type is void. Initialize from initializer, and it takes in a shared pointer to a frame hashing, which is called new frame. Okay, next we have a method to set the marginalization flag for frames need to be margined. I think we write a marginalization flag for the frames that need to be margined. Maybe marginalized. Okay, there's a parameter param new FH. It will return void and is called flag frames for marginalization, and it takes in a shared pointer of type frame hashing and a reference to new FH, new frame hashing probably. Okay, next we set the map point status according to residuals and host frames. The map point status will be set to out or marginalized according to some conditions, and if so, they will no longer be used in optimization. Okay, so the map points will have a specific status, for example out or marginalized, or I think also the out of bounds, which will tell us something about this point. And the method is of return type void, flag points for removal. Okay, the next ones are simpler. So here we remove the outliers. Void remove outliers. Then we have set precalc values. Return type void, then set precalc values. Very cryptic, but one can imagine what this does. Then we have a bigger method which solves, and there is a comment eventually migrate to EF. I don't know what they mean by EF. I think this might be energy functional, which will be, I think, a different data type which we need to implement. And they obviously think about migrating this method to a class internal method, which can make sense, of course. Add param. There's a parameter iteration, which is the number of iterations. And there's a param lambda, and lambda of LM iters. LM is not explained here as well, so I think, so in my view, that stands for Levenberg Marquardt. Oh my gosh. Okay. Marquardt. I think it's written like that. And this is some kind of optimization algorithm. So there's Gauss, I think Gauss-Raphson, Gauss-Newton, gradient descent, and Levenberg-Marquardt is the best of it. I don't know. It is actually pretty awesome, as far as I know. And it's used all over the place for almost every Visual SLAM system. So this return type is void, solve system, and it takes in an integer for the iteration and a double value for the lambda. So this solve system was mentioned in a comment before. So this will be one of the central methods we will use. Okay, and another thing was also mentioned is this one here, linearize all the residuals. It takes in a param, which is called fix linearization. If true, fix the Jacobians after this linearization. And there's a return type, which, yeah, is not explained in the original code base. So, yeah, I only know that there's a 3-vector of, let's add a to-do here. So this is a vec3, linearize all, and it takes in a bool for fixed linearization. Okay, and then we will have a reducer for multi-threading. So return type is void. Name of the method is linearize all again, but this time reductor. It will take in a bool, fixed linearization, It will also take in a standard vector of type shared pointer, of type point frame residual, with a pointer to remove. It will also have an integer with min and an integer with max, and will have a vec10 with a pointer to studs and an int tid. This sounds very similar to the other reductor we have written, which also had something to do with the multi-threading. So this reductor is very similar to this reductor for the activate points multi-threading reductor. Okay. Next we have some optimization related methods. For example, step from the backup data called in optimization. This will return a bool, do step from backup. It will take in a float step fac_c. Float step fac_c and a float step fac_t and a float step fac_r. And that's not enough. Float step fac_a. And let's see, is there something else? Ah, of course. There's also a float step fac_d. Okay, what could this mean? CTRAD. I have no idea. We will see. Then we have another method, set the current state into backup. It will return a void and it's called backup state. Takes in a bool, backup last step. Then we also want to load from the backup state. Void load state backup. Okay, I think this is a typo here. Load state backup is probably called load state backup, but I do not want, especially in the full system, I do not want to mix a little thing up and then not be able to fix that later. So unfortunately I will leave that here, but I will at least add a to-do. Maybe typo. Load state backup. So that it can be fixed later. Okay. So we back up the state, we load the state backup. Next we want to compute the energy. So energy computing functions called in optimization double calc L energy and once again we have the same comment with another double calc M energy. So there's an L energy and an M energy. and I still don't know what this means yet. Return type of the next method is void apply res reductor. And this takes in a bool, copy Jacobians with int min, int max, and once again a vec10 pointer to stats and int tid. So again the reductor, so it seems that the reductor at least, even though it's something I do not really understand yet, has at least the same signature. But the first argument is different here, it seems. Okay, then we have a standard vector of type vecx. So a vector which has a varying number of dimensions. And a method called get null spaces. And it takes in a standard vector of type vecx with a reference to null spaces pose. And similarly, we have null spaces for the scale. So there's some hint to the scale here at least. And we have the affine, FA, and FB. The affine lighting parameters. Okay, so we can get the null spaces for each of them. And we'll get a vector of vecx's. Next we have a void which sets set new frame energy th. Then we have a method that makes a new keyframe. Void make keyframe, which takes in a shared pointer of type frame hashion FH. Then we also can make an ordinary frame. Void make non-keyframe of type shared pointer frame hashion, which takes a reference to a frame hashion. Next we deliver the tracked frame to make keyframe or make non-keyframe. If we do linearization, here we will call make keyframe or make non-keyframe. Otherwise, they are called in mapping loop. Okay, as the name suggests, we want to have a void deliver tracked frame, which takes in a shared pointer of type frame hashion FH and a bool need KF. Okay, so probably when need KF, so need keyframe is true, then it will call make keyframe, otherwise it will call make non-keyframe, I would suppose. Okay, next we have a mapping loop that is running in a single thread. And this is of return type void and called mapping loop. Okay, so similar as we did with the main function here, we have defined a standard thread, which is called run thread. And in this run thread, all the images are processed. And for every image, later, when we finish it, the full system is getting called with the method called addActiveFrame. And similar to that, we'll have a mapping loop, which will do similar stuff for creating the 3D map. And this will run in a single thread, similar to the tracking loop, which we'll probably also create in a minute, and the viewer thread. Okay, next we will have to print the residual in optimization. This will return void. It's called print opt res, and we'll take in a const vec3 and a reference to res, double res l, double res m, double res prior, double le exact, okay. And of course it will also take in a float A and a float B. So let's reorganize that. We have the residuals and we have the double L exact and float A and float B. Okay, that's it for the first part of this full system definition. Now we will continue with the fields. So we have defined the methods here, which I think are not all of the methods, but the ones that are related to the pipeline. So there's already a lot of them. If you take a look, we have something related to energies, we have something related to the optimization in general, we have outliers, we have something related to points, to the frames, we have traces, we have tracking. Yeah, there's a lot of stuff to keep track of, literally, and we already can see that this is quite complex. And this is only the header file. So the implementation will have about 2000 lines of code. Not sure if we can tackle this today, but we will try to at least get something done today. Okay, next we have the fields, attributes, and variables. In the public scope, we have, to begin with, a shared pointer of type camera, which is called the H calib, and it's initialized to the null pointer. And this contains the calib information. So we need to have a way to access our camera calibration. So this will probably be stored in this H calib file, which is related to a specific camera, which then is related to a frame, and this is related to our images. In the private scope, we have data. Simple as that, we have some data. And here we have some comments that explain us what kind of data do we have. We have data that is changed by the tracker thread. And it's protected by track mutex. So we have things specific to the tracking of the camera. That is, we have a mutex called track mutex, and we have a shared pointer of type course initializer, which is called course initializer, but with a small c, and is equal to the null pointer. Then we have a vec5 called last course RMSE, and we have a vector of type shared pointer of type frame with all frame history. That is, all recorded frames. Then we have a different region, which is changed by mapper thread. So we have the tracking and the mapping loop or thread, and this is protected by the map mutex. So we create a mutex called map mutex. Simple as that. Then we have a different region which is not named, unfortunately. And here we have, it seems, things, all the general things, like things related to the energies, to the optimization, to the points, to thresholds, like everything. So I will name that general data. Here we have a shared pointer of type energy functional called EF, and this is initialized using the null pointer. Then we have an index thread reduce, which has a type vec10, and it's called thread reduce. So this EF is optimization, and this is multi-thread reducing. Next we have a shared pointer of type course distance map called course distance map, and this is equal to the null pointer. This is the course distance map, as the name already says. And we have another shared pointer of type pixel selector, named pixel selector, equal to the null pointer. And this is, who could have guessed, pixel selector. Then we have a float pointer to the selection map, which is initialized using the null pointer again. And this is selection map. Okay, next we have all frames. So we have a standard vector. Of type shared pointer, of type frame, named frames. And here are all active frames only changed in marginalize frame. Marginalize frame and add frame. I think that add frame should be add active frame. So I'm not sure if this is maybe a typo. I think I will add it here. Add active frame. Because I think there is no method called add frame. Okay, then we have the mutex for the frame. So mutex, frames, mutex. This is the mutex to lock frame, read and write. Because other places will use this information. So once again, we need to add this mutex lock to protect data that can be changed or used in different threads. So we need to protect the data. Then we have active residuals of type standard vector, of type shared pointer, of type point frame residual, called active residuals. Then we have a float, which is called current min act dist is equal to 2. Whatever this 2 means. What unit? So this is unfortunately often the case that we have variables which just have magic numbers and we do not know what those magic numbers mean. Usually they are thresholds, but oftentimes we could add some units to that to make it more clear what that means, and this is unfortunately not always included. Next we have a standard vector of type float called allResVec, which is probably a vector which contains all residuals. I will add that here, contains all residuals, just to make it explicit. Even though I'm not sure if this is really what this means, but given the context I would say that this is what it means. Next we have the frames, we have the active residuals, we have this magic number, okay, now we need another mutex, etc. for tracker exchange. So there's a mutex called course tracker swap mutex, and this means if tracker sees that there is a new reference, tracker locks. What does it lock? the course tracker swap mutex and swaps the two. Okay, if tracker sees that there is a new reference, tracker locks the course tracker swap mutex and swaps the two. Okay. Next we have a shared pointer, course tracker, which is called course tracker for new kf is equal to null pointer, set as reference. Set as reference. Okay, interesting. Protected by course tracker swap mutex. I think I will delete this one of the s here. Okay, and then we have a shared pointer, again of type course tracker, which is equal to null pointer. And this is always used to track, new frames, protected by track mutex. Okay, then we have a mutex for shell pose mutex. Then we have tracking and mapping synchronization, all protected by track map sync mutex. Therefore, we need this, so we create a mutex track map sync mutex. Then we have a condition variable called tracked frame signal, and we have another condition variable called mapped frame signal. And here we have the dequeue of type shared pointer of type frame, which is called unmapped tracked frames. Then we have an integer which says need new kf after is equal to -1. Need new kf after, and the explanation is otherwise a new kf keyframe is needed that has ID bigger than need new kf after, I think. Okay. So in the beginning, the need new kf after is -1. That means that probably this one indicates that it has a lower ID than the new keyframe, and therefore probably in the beginning a new keyframe is being created, and then it continues like that, and new keyframes are added by some kind of heuristic. And after some frames have been processed, we have a certain number of keyframes, which will also probably change during the operation. And yeah, this is important information that we need. Next, we will have a thread, which is our mapping thread. We will have a bool run mapping is equal to true. And we will have a nice bool called need to catch up. Need to catch up mapping is equal to false. Okay, so we need to catch up mapping. Let's add a to do. Catch up is equal to catch up. Even though it's kind of funny that it's called catch up. It's a nice idea. Next we have a public section. Once again, which contains a shared pointer of type map and is called global map and is equal to the null pointer. So this is our global map. Then we have a feature detector called detector. This is our feature detector. And then we have another region, which is called loop closing. There's another public area, public scope, which contains a shared pointer of type orb vocabulary called vocab is equal to the null pointer. So this is our vocabulary. And we have a shared pointer of type loop closing, which is called loop closing, is equal to the null pointer. And this is the loop closing. Then we have a region for visualization. Which will also have a public scope, where we have a method called setViewer, which takes in a shared pointer of type pangolin DSO viewer and is named v. And here we say we set the internal viewer equal to v and check if the viewer is set. Then we say viewer set map to the global map. Next we have a private scope with a shared pointer of type pangolin DSO viewer called viewer, and it's equal to null pointer. Then we have a region which is useful for debugging. And here we have a public scope again. Which will save the trajectory in TUM or UROC format. It takes in a parameter, file name, and another param, print optimized, which will print the trajectory after loop closure. And here we return void and say print result. And we take in a constant string for the reference to the file name. And a boolean for print optimized, which is usually equal to true. Next, we also want to, besides the TUM and UROC data format, want to save the trajectory in the kitty format, which is the other data set that is usually used. But there's a note here. Note, we only save keyframe poses. Not all poses, so they cannot be directly evaluated by Kitty's default program. And there's the information which also ignore the scale issue. So again, the scale is a very important topic here. For monocular cameras, we usually cannot determine the absolute scale, only a relative scale. And they claim in this comment that the default program of Kitty ignores the scale issue, whatever this means. But this is important to know. Okay, and the method is not called print result, but it's called print result kitty. It takes in the const string reference to the file name, and bool print optimized is equal to true as well. Okay, next I will move this comment a bit further up. Maybe, where do I put it? Maybe here, before this mutex for the tracker exchange, because from here on we have very specific thread related variables, although not really. Oh well, let me remove this comment that I wrote here. It does not really fit here. Okay, let's save that. And we are actually finished with the header file. This was the easy part. Let's take a drink. Okay, the good tea. All right, now what can we do now? So we have a big problem here. That is that we almost do not have anything from the data types here. So we do not have a frame Hessian. We do not have this imager point. We do not have the imager point temporary residual. We do not have the point Hessian. So usually we would need to do or to encapsulate everything within a to-do. I'm thinking now about still writing the implementation for the full system such that we have everything available code-wise, and then in the next parts we can implement the frame header file, the point header file, the feature header file, the camera header file, the viewer, which will also be very important so that we can finally see something on the screen. We'll have the map, the feature detector, feature matcher, and pixel selector. And we then have to do some threading related stuff and the loop closing. So now that we are in the thought process of knowing what the full system contains, like from a very high perspective from this header file, I think it would make sense to now continue with the implementation. Okay, let's do it now. Good. So we have the include file that we have now finished, which, as I said, would need a lot of modifications to add those to-dos everywhere. But for now we will just add in the source directory and then in the front end, just as with the include directory here, we add into the front end a new file which is called FullSystem.cc. And now let's see. So we want to include several things here. And those are usually all things that we have implemented ourselves. So we include the feature.header file. And we also include the frame header file and the point header file. Then we will include from the front end the FullSystem.h file. We'll also include from the front end the course initializer.header file. Then we have the front end and there's a course tracker header file. And there is in the front end a loop closing header file. Then we have the internal directory. It will contain an imager point header file. It will also create, or it already does contain, the global calib.header file. And it also contains the global funcs.header file. And it also will contain an optimization backend. And there is an energy, or there will be an energy functional header file. Next we have some libraries like the OpenCV library, OpenCV2/features/features.hpp. It's a features2D HPP, I mean. So here we will get our functions to detect the features in the images. I think this will be orb features, but we will see. So next we have an IO manip library, and we have from OpenCV again some something about the high GUI, high-GUI.hpp. So these will be functions for either displaying or opening windows, for displaying images, or also drawing functions, I think, like drawing circles and rectangles and similar. Okay, next we are using some namespaces, namely using namespace LDSO and using namespace LDSO internal. Okay, now we are opening up the namespace LDSO, and here we are defining our implementation for the full system. That is, we start with the constructor. So we write full system and full system again, and this will take in a shared pointer of type orb vocabulary called voc. And then we want to initialize the variables with initial values. So we want to initialize the course distance map with a new course distance map, which takes in a WG at position 0 and an HG at position 0. So I think the WG and HG are arrays that contain the specific image resolutions from the image pyramid. So depending on how many image pyramid levels we have, so if we go back into where we have tested this implementation, you saw several times that we are using pyramid levels 0 to 3. And the course's resolution is 80 by 60, whereas the full resolution is 1280 by 1024. And we have those image resolutions stored in this data structure that is used here in this WG. I think this WG was specified before in a previous video in the global calib here. Yes. Here you can see that if you open the global calib header file, you will see that there is an extern integer WG with the total number of pyramid levels and HG with also the total number of pyramid levels. So here we want to get the pyramid level 0, which should be, in my view, the finest. Therefore, WG would be 1200 and let me quickly look that up. 1280 for the width and 1024 for the height. So we initialize the coarse distance map by the image resolution, which makes sense if we have like a depth map. I would probably call that coarse depth map and not distance map, but maybe that's a different meaning here. We will see that. Then we have various other initializations, for example, for the coarse tracker, which will be initialized using new coarse tracker, which also takes in WG0 and HG0. Then we have the coarse tracker for new KF, which is a new coarse tracker, once again, with the same dimensions. Then we have a coarse initializer, which will create a new coarse initializer with the same dimensions. Then we have to initialize EF, which is a new energy functional, which takes in no arguments at all. Next we have an H calib, which is, as far as I remember, the camera calibration, which takes in a new camera. And this one takes an FXG at 0, FYG at 0. So these are the focal lengths in X and Y, the global ones, therefore G. Next we have CXG0, which is the principal point in X direction, and CYG at 0, which is the principal point in Y direction. Next we have a global map, which we initialize using new map, and we pass this to the map. And we want to initialize the vocab using the past voc. And this is all about the initialization of the member variables. Next, what do we want to do here? First, when the full system is being created, we want to print something to the console. We want to print what the user of the Visual SLAM can see here. So we log using the Google logging library as an info, and we print the following. I will create a new line. And we write as follows. This is direct sparse odometry. A fully direct VO proposed by TUM Vision Group. For more information about DSO, see direct sparse odometry by Jacob Engel and I think Vladun Koltun, I'm sorry if that is wrong, and Daniel Kremos. These are known names in the community. So to be clear, this is nothing I have done. This is from the TUM, the Technische Universität München in Munich, and we are talking about this work. We are talking about direct sparse odometry here from Jacob Engel, Vladlen Koltun and Daniel Kremos. A nice system which works really well as long as you as long as you keep in mind that there are specific assumptions for the system, like image brightness, constancy, for example, and other things. Okay. Daniel Kremers in. Let me copy that. In archive X from 2016. I will I will reorganize this comment a little bit so it's easier to read. For loop closing part C LDSO, that's direct sparse odometry, with loop closure. This is from X Gao, R Wang, Nikolaus Demme, and again Daniel Kremers. And it was published in International Conference on Intelligent Robots and Systems, the IROS, in 2018. End line. So, usually very recent stuff. I mean, things are moving very fast, especially with the machine learning stuff, like deep visual odometry and neural radiance fields and whatnot, but still very relevant. Okay, next we want to initialize the h-calip. No, not initialized, it is already initialized in the constructor, but now we want to use something. We want to create a ch, which is probably a calip hashing, and we want to pass the h-calip. h-calip. Then we have the last course RMSE dot set constant 100. Let me comment that maybe here with create calip hashing ch. And this last course RMSE is a vector, I think. A vec5, so let's add it here. Initialize vec5 with, I think, all 100 values. Like this. Let's keep it a little bit more verbose that the original code was. Then we have the energy functional, and there's an attribute ret, which is equal to a reference to this, and then thread reduce. So ret is standing for reduce, used in multi-threading. Then we have a mapping thread, which is equal to thread from end full system mapping loop and this. Then we have a pixel selector, which is a shared pointer of type pixel selector. that takes in a new pixel selector with WG at position 0 and HG at position 0 as well. So basically our image dimensions in the finest level of the image pyramid. Then we have a selection map, which is equal to new float array, which is initialized using the image dimensions as well. So WG at position 0 times height, global height at position 0, at level 0 from the image pyramid. Then we check if setting enable loop closing is true. And we say loop closing is equal to the shared pointer of type loop closing, and we initialize it using new loop closing based on this. Then we check if setting fast loop closing is true. Then we log an info that is use fast loop closing. Then we end the line. And if we do not have loop closing enabled, then we log info that loop closing is disabled. And we end the line. And this is the whole constructor, which is not a lot, but of course a lot is happening when we create the new course distance map, the new course tracker, course initializer, energy functional map, and camera. So without those data types implemented, we will not be able to test the full system, unfortunately. So I think we will tackle the next in the next parts. We will tackle those data types primarily, so that we can quickly test at least this this line of code here, which is here creating a shared pointer to the full system. Although, yeah, it should be possible. So I thought maybe it's not possible because in the header file there is a lot of other things contained, but we can comment that out and then at least create a full system which is not functional, but we at least have this data structure then. So I think this will be the goal for the next videos. But for now we will continue even though we do not have almost everything. Okay, after this constructor, we will create the destructor. So we create full system and then full system. And here we want to block until mapping is finished. Then we also need to remember to release the inner structure. That is this unmapped tracked frames dot clear. And if we have the setting enable loop closing, this is equal to false. Then we want to delete the whole array of the selection map. And else we do nothing. Therefore I will not even write it here, even though in the original code it is just an empty else block. Okay, so this is the destructor. Now we can move on with the next method. So the next very important method after the constructor is of course the void FullSystem and then add active frame. This one takes in an image and exposure pointer to an image and an integer of an ID. So this one, I cannot stress it enough. This is very important method. Entry point from main loop. So here in this add active frame, we start with the Visual Slam magic, so to say. What does that mean? So if the system is lost, then we want to return. And this means that once the system is lost, it is lost forever. It will not recover. Therefore, we have no relocalization in the LDSO, and it can in general be very sensitive to the data we provide to it, which can be a disadvantage, or I think we can clearly say that this is a disadvantage, but still the whole system in general is quite nice. Next we have a unique log of type mutex, where we say we log based on the track mutex. Next we log an info which looks like that. So we have those 3 stars, and then we say taking frame, and then we pass in the ID, and then we say 3 stars again, and then we end the line. Like this. Next we create frame and frame hashion. So there's a shared pointer of type frame, which is called frame, and we pass in a new frame which takes in as the constructor argument from the image timestamp. So we can simply create a new frame from a timestamp, which is something good to know at this point. Then from the frame we call create FH based on the frame. And this is probably a frame hashion. FH is frame hashion. Then we have the all frame history. We push back the current frame. Up until here it's very simple. Next we make the images. So we have a shared pointer. of type frame hashing, which we call FH. And this is equal to frame, and from the frame we take the frame hashing. Then in FH we say AB exposure is equal to image exposure time. Also very simple. And we say FH make images. That is, from the image we pass the image, and from H calip we pass the MPCH. So MPCH is not clear to me. I think CH maybe calip hashing, but what this MP means, maybe map calip hashing, not sure. Okay, next we check if we are not initialized. So we are now talking about the full system. If the full system is not initialized, which will be the case in the beginning, then we do the following. We log an info that we are initializing ... Then we end the line. Next we use the initializer. We check if course initializer frame ID is less than 0. So if course initializer frame ID is less than 0, this means that we have the first frame not set, therefore set it. So course initializer set first H calip and then MPCH, and we pass in the FH. So set first is, as far as it looks, takes in the camera calibration and the frame, which makes sense because with this we can create, for example, the projection matrix. We can anyway set the initial translation and rotation of our camera and the scale probably as well. And yeah, this way we can just set the first state of our camera. Else if, so if the course initializer can track a frame, track frame FH, this means if it can track that frame, this means that the initialization or init succeeded. Now we can call initialize from initializer and pass the frame hashing. Now we can say log.unlock. Now we can deliver the tracked frame FH and true. This means that we want to create a new keyframe, and then we log an info which tells us init success. End line. But else we are still initializing. We are still initializing. And This means that the frame pose valid is false. And we say frame release all. Which means that don't need this frame release all the internal. So if we cannot track a frame, it seems that we are just throwing away this frame. After the else block, we return. Because the rest that follows here should not be done. But first we need to add an else block to this if not initialized. So in the other case, if, so else, if we are initialized, so that is init finished, then we want to do the tracking. And that is swap tracking reference question mark full stop. So I don't know if this is a question from the authors or if this is like a statement, but we will find out. So here we check if course tracker for new keyframe. From this, the ref frame ID is greater than course tracker ref frame ID So if the reference frame ID from the course tracker for new keyframe is greater than the one from the course tracker, then we want to have a unique log of type mutex called CR log, and it takes in a course tracker swap mutex. Then we log an info, namely swap course tracker to course tracker like this for new KF, and from that ref frame ID. And then we end the line and we create an auto temp is equal to course tracker, and then we say course tracker is equal to course tracker for new KF and course tracker for new KF is equal to temp. So this is a usual swapping operation as you learn in your programming course. So we are actually swapping something related to tracker, but is it the reference? I think we are swapping the course tracker here. We are swapping the course tracker based on frame ID. Something like that. Okay, next we want to actually track the new frame, track the new frame, and get the state. So we log an info called tracking new frame, and we end the line, and then we have a vec4 tres is equal to track new course of frame hashing. Then we check if not standard is finite cast to double tres at position 0, or then we copy that. So if not is finite, double tres 0, or is not or not is finite, double tres 1, or not is finite, double tres 2, or not is finite, tres 3. What do we do here if they are not finite, those values? Then we have an invalid result. So we have to log a warning which says initial tracking failed, lost, and then we end the line. We also need to say that this full system is lost, so we set it to true, and then we return, because we cannot do anything else. Next, we create a bool need to make kf is equal to false. So we assume we do not need to make a new keyframe. If setting keyframes per second is greater than 0, then we need to take a look at the time. So we say make keyframe by time. So we set the bool need to make kf equal to all frame history dot size is equal to 1. So that means if we only have one frame in our history, then we want to make a new keyframe. Or if frame, and then from the frame the timestamp minus all the frames dot back, so the last one, from this the timestamp is greater than 0.95 f divided by setting keyframes per second. Okay, so this is not set to 1.0 but 0.995. That means that we are actually creating a keyframe a little bit earlier than the actual setting is saying that we should do. Okay, so we determine if we need to make a new keyframe. And if the setting is equal to 0, so the setting keyframes per second is equal to 0 or less than 0, then we say else. We want to do something else. And that is, we now want to create a vec2. This is called ref2fh. And this is equal to f light, which is not defined yet. And here we have, it seems, a static method from to vec exposure, which takes in the course tracker, and from this the last reference, last ref, and from this the AB exposure. Then we have the FH, and from this we have again an AB exposure. So we have the AB exposure from the course tracker, last reference, and from the frame Hessian, which is the current frame, as far as I understand it. And we also take the course tracker, last ref, and here we take, oh, it's a last ref, and then directly after that F, G2L, and we also pass the frame Hessian, F, G2L, which is a function call. So we create this interesting vec2 here, which will have some sort of information about our A and B exposure time values and our probably gamma response, which is converted to an L, which is probably something like lighting or something, or affine light. Yeah, we will see that once we have implemented that. Then we create a float B, which is equal to setting kf global weight times the setting max shift weight t times square root for floats, which is cast to a double, and we take the tres at position 1 divided by the width, the global width at position 0 plus the global height at position 0 added together, and then we add similarly like that we add basically the same. So we have this expression, we have the global weight times the max shift weight times the square root of tres1 divided by width plus height. And then we add the same setting kf global weight times the setting max shift weight, but not t, but r. Ah, hi, hey, how's it going? How's it going? Nice. I think it's going quite well. Thank you very much. Have fun watching. I'm currently implementing the FullSystem.cc file, which is very cryptic, but we're getting there. I have a code line number 162 from approximately 2000. So there's a lot of work to do still, but thank you for asking and have fun watching. And if you want to, if you have something to report from your own work, feel free. I will try to then comment it. Other than that, have fun watching. Okay, so now we have the global weight again, times the setting max shift weight R. Thanks. Okay. Times the square root of the TRES 2 divided by the width and height added together like this. Okay, the next line is again setting KF global weight times setting max shift weight, this time not T and not R, but RT, and then times square root of double TRES 3 divided by width plus height. And lastly, we add again the KF global weight times setting max shift, and this time not max shift but max affine weight times F absolute of, now it's getting really interesting, let me get rid of that, FABS of log F of cast to float ref to FH at position 0. And that's it. Yeah, so a lot of stuff is happening here, which I do not fully understand. I'm not sure what this T and R, maybe it's translation, rotation and translation. And this is the like the image brightness factor here. But adding all of this together, yeah, is interesting. Let's keep it like that. Okay, next we define two new bools. B1, which is equal to B is greater than 1. And another bool, B2, is equal to... Dang, what's that B float for? Well, that's a very interesting question. Great that you ask. I have no idea. we will find out. So it's somehow used in this B1 definition here. So if this B is greater than 1, then this B1 is true. And B2 is set to 2 times course tracker. And from course tracker we take first course, if I can type, RMSE is less than TRES at index 0. Yeah. Cryptic as well. I think we can play with those values and adjust certain things, but not sure if this will change anything that we can see later. But anyway, we need to make the keyframe if the all frame history dot size is equal to 1, or oh, so we got like an UML which you convert to code. No, I'm actually retyping the original code base from the LDSO, so I can show you that. So this is direct sparse odometry. It's the abbreviation, or this is the full name for DSO. And there's also the LDSO, which is the next version. I will quickly look it up. So this is this one here. So this is the direct sparse odometry with loop closure. And what I'm doing is I'm looking at the original code base and I'm coding it up from scratch based on the original code with the hope to be able to learn it this way. And I feel like I'm learning something, but yeah, maybe it's not as efficient, but that's what I try at the moment. So I have no no model drawing, no UML diagram or something. I'm just using the previous code, and I'm trying to step by step implementing it and testing it so that I can slowly see how the whole story unfolds, so to say. I hope this makes sense. If not, please tell me. Okay, or B1 or B2. So, to answer your question, the float B is just one indicator, similar like B1 and B2, that tells us if we need to make a new keyframe. That's basically the answer. Okay, so what do we need to do next? So after we have checked if we are setting the keyframes per second or not, we have basically determined if we need to make a new keyframe. So given those settings, we have specific heuristics which tell us that, and from this we now know if we need to make a new keyframe. After that, we are going to the viewer. So if we have a viewer, then we say viewer publish cam pose. And this is our connection to showing a new camera pose, or the actual tracked camera in the viewer. And therefore we of course need to pass the current camera pose to it. And this is done by writing FH and frame. So from the frame hashion, we take the frame, and we also need the H calip, and from this the MPCH. So we need again a specific frame, and with the frame there is the information about the camera pose, and we need the camera calibration to actually draw the camera and display it in the viewer. And to remind you what this means, let me see if I have this video somewhere. No, it's not here. Well, maybe let's go back here. Like from this video. So this is what we are trying to code. I saw your question, I will answer it in a minute. Just wanted to say here this camera. So if you take a look at this video, you see that these cameras are displayed, and when we call publish cam pose, we are just drawing a new camera, I would say. I'm not sure. We will find out exactly at some point, but this is what we are going to, what we are trying to do here with the full system, at least. Now your question, doesn't one or something else always equal true? Let me check. I think it's not the case here. So here you have this one. This would be true if I would delete this part, like this. If this would be like that, then yes, you would be right, or you would be correct with this being always true. But we are actually checking if the allFrameHistory.size is equal to 1. So if we currently only have one frame in our history, then this evaluates to true. But if we have 2 frames or 3 frames or something else, then this will be false, and only the other values like B1 and B2 can lead to this need to make new keyframe evaluate to true. That's how I would interpret it. Maybe I'm wrong, but yeah, that's my view. Yeah, Yeah, it's easy to overlook that. Yeah, you're right. Okay, we want to publish the cam pose. And thank you, by the way, for engaging in the chat. It's nice to have. It's nice to have audience. The last parts, I was sitting here alone, and now I have friends. No, just kidding. Okay. Now we have to lock. We have to take the lock and unlock it. So this is our mutex lock, which we have defined somewhere. Where is it? Lock. Here, this unique lock. Oh no, it's the CR lock. It's probably something else. Ah, it's from the beginning of this important add active frame method. So here, this lock will be unlocked if we are at this point, because we are almost finished with this method. Nice face. Here we take log info and we log that we deliver the frame with frame hashion, frame ID, end line. Then we deliver the tracked frame with the frame hashion and the information that we need to make keyframe. And we also log info with add active frame returned, and then end line and end line. Next we return. So this is what the very important add active frame method is doing. Let's quickly recap it. So we create the frame and the frame hashion, which will then be used to track the frame. Next we also set the exposure time of the frame hashion and make specific images. That is, I think that we can later take that in the viewer and display the images just the way that it was displayed here. So in the graphical user interface we will also see at least the current frame and a keyframe, and we want to display that in the viewer, so this should be stored in the frame hashion, and this way we can later quickly see if everything is going correct or not. Okay, so and then the tracking is happening, and we have some heuristics to define if we need a new keyframe, and we publish the camera pose to the viewer, and that's basically everything. Simple. Obviously not, but yeah, it can be simple if one understands it, which we try to do here. Okay, now we continue with the next method, which is from the full system and called deliver tracked frame. We have used this here in this add active frame method, so we now need to define it, and this takes a shared pointer of type frame hashion, just FH. Yeah, very simple, obviously. Duh. Yes, isn't it? Bool need KF. Okay, so here we have a frame hashion and this bool that we need a keyframe, and this is called like that in, for example, the add active frame. Then we have if we linearize the operation And if we need a keyframe, then we of course make a keyframe. Again, very simple. And else, what do we do if we do not need a keyframe? Who can guess it? What do we make? Well, of course, a non-keyframe. I don't know, it's not really that funny as I'm predicting now, or what's the name? I don't know. Let's continue. Okay, so if we linearize the operation, we say, do we need a keyframe? If we do need one, we make a keyframe, else we make a non-keyframe based on the frame hashing. And if we do not linearize the operation, so else, we have a unique lock. Unique lock mutex. Create a lock based on the track map sync mutex. So with this lock in place, we say we have the unmapped tracked frames dot pushback. We take this current frame hashing. From this we take the frame and put it in the list of unmapped tracked frames. And we say tracked frame signal dot notify all. So we say that we have a new tracked frame, so we notify everyone that needs to know that. And then while the course tracker for new KF ref frame ID is equal to -1 and course tracker ref frame ID is equal to -1. So if both course trackers have a reference frame ID of -1, then we log the info that we wait for mapped frame signal and end the line, and also take the mapped frame signal and wait using the log. And after this while loop has finished, we say log, unlock. And this is the whole deliver tracked frame method. Next, we want to have a method that can track a new frame. And this will return a vec4. It's full system. Track new course. It takes in a shared pointer of type frame hashing, FH. And what do we want to do here? First of all, we want to assert. We want to assert if all frame history dot size is greater than 0. So if this is greater than 0, this will return true, and assert true will then let us continue with this method. Next, we create a shared pointer of type frame hashing, which is called last f, probably last frame, is equal to course tracker last ref. Then we have this check macro, which I do not know. Check. Somehow defined, probably not. Course tracker. Last ref. Frame. If this is not equal to null or null pointer, then something will happen. I think we will somewhere define this check macro. I cannot see where it is defined at the moment, so I hope we will not forget that. Next we have affine light parameters, flight, which are called f last to L, which is equal to f light, and we initialize that by 0, 0. So this is a class we also need to create in the future, but this will probably contain the A and B parameters, I think, which are contrast and brightness of the image. But I'm not sure, I have not implemented this yet, so this is still a question mark here. Maybe let's say like this. But those A and B parameters are very important because they help us to adjust the image intensity in such a way that we can fulfill the cost function in the optimization procedure that will help us to determine the actual camera motion, and the 3D point location for our specific dataset. So if the image brightness is changing a lot, then those A and B parameters will also change a lot. And if we have perfect images generated in Blender, for example, in simulation, then this will probably not change at all. But this is something we can test once we understand how the LDSO is working. Yes. Wow, implementing the class later, you're ready. Yeah. Yeah, I thought about if this makes sense. You're right. Usually we should implement the classes first and then use it, or use them, of course. But I think at this point it would be nice to have the big picture, like seeing how everything is organized, and then I have the feeling that we have a better understanding what the actual frame hashing, f-light, and yeah, FullSystem at all, what they are actually useful for, or what they are doing. But I'm not sure if this is the right way to do it, okay? I don't know. You probably know it better. I will just try it this way, and then if I notice that this was not a good idea, then at least I have learned something. Yeah, we will see. It's definitely something, hey, no front, I know, but it's something one can definitely criticize. So if this is the right approach, yeah, it's just an experiment. We'll find out together. That's very nicely said. Thank you. I like that. Okay. Now here is something is happening. Here's something really nice happening. So if you are watching, if you're still watching, please watch for the next maybe 5 to 10 minutes. You will see something really, really awesome. If you do not know the LDSO code, I think it's the most amazing part from the LDSO. Let's see. Maybe I am teasing you a lot, but we're in this together now. That's just yes, so true, so true. Okay, now look at this comment. Try a lot of pose values and see which is best. So basically what the LDSO is doing here, we do not know what is the correct camera motion. So what do? We just try a ton of different configurations and we just hope for the best. This is the amazing part in my view. Okay, so we make a new standard vector which contains an SE3, so a special Euclidean group, Lie group, with the eigen library, and from this we have the aligned allocator of type SE3 as well. And we name that thing last F to FH tries. Okay? So this is the last frame to frame Hessian, which is the current frame as far as I understand it. And then we have tries. So here we store the try a lot of pose values basically. Okay, first we check if all frame history dot size, if this is equal to 2, then we do what? We make a for loop. We start with an unsigned integer. I is equal to 0. I is less than last F to FH tries dot size and I plus plus. And here, interestingly, there's a comment to do. Maybe wrong. Size is, I have to check if this is something I have added. Size is obviously 0. Interesting. Okay, maybe wrong. Size is obviously 0. Yes, that's true. We have just created this tries and this is 0. So this will never be executed. Yeah. Very true. But this is in fact something that happens in the LDSO code. Last F. Still we continue. Last F to FH tries. Push back an empty SE3. So here's the comment use identity. So maybe if you want, you can try, you can write it in the chat. Do you all know what an SE3 is? I'm very interested in knowing if you know what an SE3 is. Okay, so if, and here there's an else. Else we want to fill the pose tries. That means use the last before last and the last before last. Well, my English is really poor. That's really in the code here. Well, my English is really poor. That's so funny. Yeah. Okay. Nope, no idea. And it's a Lie group. Yes. Is the SE3 object just a pose here? Yes, I would say. SE3 contains translation and rotation. And the SE3 type is defined in this num types header file. Somewhere. Here. So here we have the poses that they are represented as Sophos structs. So we have the Sophos library, which is shipped with the LDSO. It's a header only library, I think. And in Sophos we have an SE3 and then a Sim3. And if we have an SE3, we also have an SO3. And those are defined here. So these are the original data types. And these are the new data types that we override here basically. So we have SO3, which only contains a rotation. Let's write it here. So this is a special orthogonal group. Then we have rotation and translation. This is a special Euclidean group, and this is a rotation, translation and scale, which is a similarity group, I think. Not sure at the moment. Sim3. I think it's similarity group, but I'm not sure here. Sorry about that. Yes, and we have our camera that is moving through the space, through 3D space. We represent each camera pose using SE3 data types. And yeah, we need to somehow fill them up here. And this is what comes here, and this is the interesting part. So even this comment was quite nice, I have to admit. But now we create the data structures. So we make a new shared pointer frame, which is called asLast. And this will be initialized using all frame history with all frame history dot size -2. And similar to this, we have asPreLast, which we take from all frame history dot size -3. Okay. So we take from our all frame history, from the end, -2, the pose, and the one from the end -3, and store them here. And this will be used to estimate the next or the current pose. Therefore, we need to create new SE3 objects, asLast to asPreLast, and then SE3 last F to asLast. Then we have to lock. We have to lock on global pose consistency. So we want to make sure that we are not changing values in another thread. So we need to create a unique lock of type mutex, and create a CR lock with shell pose mutex. So this is the camera pose that we want to protect here. And we say asLast to asPreLast is equal to asPreLast get pose times asLast get pose dot inverse So this get pose is usually that's a bit of a pity that it is not expressed explicitly, but this get pose should be the absolute pose. So we have the pose expressed in world coordinates, and if we take another pose and get its inverse, we are actually calculating the relative transformation, so between those two poses. And therefore this is called asLast to asPreLast. So this is the relative pose, whereas this part, for example, and this part, both are absolute poses. That's my understanding of it. Then we have last F to S last, which means we take the S last, get pose, times the last F, and from this the frame, and from this the get pose dot inverse. It is a bit confusing to keep track of that, but in both cases here, in both lines, we are just interested in the relative camera transformation. So our relative motion from one image to the other. We do not only need the poses, but we also need the affine light parameters. So F last to L, which is equal to S last F G to L, without a function call. Okay, now we are prepared to do the interesting part. So we define a new SE3, FH to S last is equal to S last to S pre-last. And here we assumed to be the same as FH to S last. So this is starting to be some kind of implementation of a motion model, which means that now we are saying, well, the current FH, so the current frame that we have, to the second last frame, it is just the same as the one we have calculated above, so the S last to S pre-last. So we basically just take the previous motion of the camera and say, okay, we are exactly moving the same way. We've prepared this here. I would maybe also add like constant velocity motion model here. Next we want to get last delta movement. So it's all about getting and extracting the previous camera motion so that we can, based on this previous camera motion, create new camera motion hypotheses. So the motion model is just fixed velocity. Yeah, I would say, well, it's one of the motion hypotheses. It's not the only one, but yes, it's definitely one of the motion models used here is like a fixed velocity. We just continue moving with the previous velocity that we have been using or calculating. Okay, then we have last frame to current frame tries dot pushback. FH to S last dot inverse times last F to S last. And here we have what you have written in the chat, Rahomo. That is assume constant motion. So it looks a bit cryptic here. But we are here in this case, not sure, it could be wrong what I'm just saying, but we are trying to add this relative motion to the one that we have previously to get a new absolute motion that we store in this tries vector, and then can use it to evaluate, well, is this the correct one, or do we need to adjust it a little bit or not? But we have, at least we have some initial values, which is very important for this kind of Visual SLAM. Okay, next we have something very similar. Here we push back the same in the beginning, and then times this again, but before that we also add FH2 as last dot inverse times last F to as last. And this one, you see, this contains double or let's say twice this FH to as last inverse. So this is not the constant motion, but this is that we assume double motion. Or we could also say a frame skipped. Maybe let me activate this word wrap here so that everyone can read what is written here. Okay, and next we also add something new, that is that we now want to, let me think. Okay, here we assumed a very fast motion. Now we want to do it by half, so we want to assume a rather slow motion. That is done by calling SE3, and in SE3 there is an exponential function, and this takes in, it's really hard because it has something to do with Lie algebras, and I always need to think how this is, what is the correct direction. So we can use SE3 Lie groups to move from groups to algebras, and this is done by using the logarithm or exponential functions. And I always forget which function is responsible for which direction, but I think I see it now. So we have FH2 as last dot log. I think this one will convert from the group to the algebra. So the log mapping will go from group to algebra. Then we can do some operations on that in the Lie algebra space. So we can say times 0.5. And then we can take that and convert back from Lie algebra to Lie group using the exponential function. And this way we have basically done our calculations very easily in the Lie algebra space. So just a multiplication. Whereas this would be maybe more complex in the Lie group space. We simply convert to the algebra by using this log method. And then we do simple calculations, and then we convert back to the Lie group space, and we have done very complex maths. That's clever, yeah. Absolutely correct. I totally agree. It's very clever. And it's nice to know that concept. When you work in robotics, I think it's very useful to be proficient in that. So here we have the inverse from that, similar to like we did in the upper versions. And we once again just multiply with this the inverse. So the inverse times FH to S last, and not inverse here. I'm sorry, I mixed up something, but it's not that crucial. Okay, it should be like that. So this is the conversion. So this is the clever trick here. Then we take the inverse, just as we did here, and then we multiply with the last F to S last. Last F to S last. Yes, and here we assume, because we have multiplied by 0.5, we assume half motion. That would be really, really hard or really time consuming if I would need to really code that up from scratch. I'm so happy that I see the original code and can think about it, because otherwise this would be very hard, I think. Okay, we have two other variations. So we have last F to FH tries dot pushback. Last F to S last. What could this be? Last F to S last. We just take the previous. Oh, well, no, we do not take the previous, but we take the identity here. So this is the identity. And this is the identity as well. We do not override that. Well, actually we do here in this part. Ah, we are just initializing it, okay. But here we are pushing it back into our tries. So that means that in this part we assume zero motion. So basically we say, okay, we are not moving at all, we're just standing still. And lastly, for this part, we have another try that we add, that is just the identity. And the important difference is that this one is from the keyframe. So we have frames. So last frame to second last, I think. S last is second last. And we have second pre-last and so on and so forth, but those are all frames. But then we can also have the relative motion from the last keyframe, so from the previous keyframe. And this is something we need to take into account here. Okay, but now, for the interesting part here, now we just try a ton of different initializations, all rotations. In the end, if they don't work, they will only be tried on the coarsest level, which is super fast anyway. And also, if tracking rails here, we lose. So we really, really want to avoid that. So I think this should be if tracking fails. tracking fails here, comma, we lose. Full stop. So we really want to avoid that. Okay, what does this mean? So rotations are usually problematic because camera rotations do not tell us something useful about the depth, the changing depth, and therefore this is usually a problem. So the approach the LDSO is taking here is to just try a ton of different of those rotations and again hope for the best, so that one of these rotations is close to the value that we are looking for. And then we are tracking on the cost level. So we are creating quite a few of those try values here. And this is not a big problem because we will then evaluate those motion hypotheses and quickly check, okay, is it okay or is it not okay in the cost level. So we have, if you take a look at the current implementation, then here we have the information that using pyramid levels 0 to 3, as I already mentioned before, we have the coarses resolution 80 by 60, and evaluating 80 by 60 pixels is by far more efficient than evaluating 1280 by 1024 pixels, for example. So this is something which is another nice thing besides those Lie algebras that are used here, is that we are tracking, or we are estimating the relative camera motion by a coarse to fine strategy. So we start with the coarse images. We see, okay, does it somehow converge? And if it does not converge, then we simply go to the next motion hypothesis here. And if then everything fails here, then we lose. So we have a lost system then, and we usually cannot recover from that. But the coarse images will give us a good indication if this is going to be successful or not. Okay, here we start a new for loop with a float where we initialize a rod delta to 0.02, and we say rod delta is less than 0.05, and we say rod delta plus equals 0.01. Oops. Okay. And here we will list our rotations. Oh, there's one to do here. To do changed this into plus equals 0.01, where DSO writes, what does it write? Writes plus plus. Ah, okay. So this is something that was changed from DSO to LDSO. Here it was just written rod delta plus plus, which of course means that it will only execute once with rod delta is equal to 0.02, but we want to have it executed quite a bit more. So this way it will execute, I think, 0.02, 0.03, 0.04, and 0.05 will not be executed, so I think 3 times or something. Okay, next we also have this tries list that we fill up here. And we do that by the following command. So we have fh2 slast dot inverse times last f 2 slast times se3, and here we take from Sophos. Unfortunately, it will not. IntelliSense is not working somehow. I don't know why. Sophos quaternion d for double 1 rot delta 0 0. So we are initializing a quaternion with the values 1 rot delta 0 0. And here the comments are all the same, like assume constant motion. Ah, I see, there's also a vector given. So after the quaternion, we have a vec3 0 0 0. Why is that? Ah, okay. Because the constructor of SE3 needs a quaternion and a translation. And the translation is initialized as the 0 vector. And the quaternion is initialized using this rotation delta with this first value, which is probably the W in the quaternion, being 1. So we are here, as far as I understand it, we are here rotating around the x-axis. Okay, I'm confused here. What axis are they rotating around? In my view, this is the x-axis here. So you have... I would need to look it up here. Maybe you can go inside that. SE3. SE3. I'm not sure if I can find it now. But there are different constructors. Ah, already answered. Okay, yeah. Okay. For the details, I would need to look it up, but probably this is like some way of defining an... yeah, I'm not sure. I'm not sure, sorry. But you will see that in the next lines, this kind of 3D vector will change. So the rod delta will move from this position to this one, and so on and so forth. So I think this looks like being the rotation axis here. But a very good question. Next, we have this inverse. So which one is it at home? I see. Yeah, I think we can clarify that in a minute by looking into the code, but you will see. If I write it down, you will probably see the idea at least. Let me just quickly check if I'm not confusing something here. Yes. Okay. I'm thinking about making this a little bit more readable here. Maybe by putting this in a new line. Okay, so what we are simply doing here, guys, is the following. We are just moving this rod delta one more to the right, like this. So you can assume that this is the x-axis we are rotating around, and this is the y-axis we are rotating around. And we do the next in a similar fashion. That is, we are just taking this part and moving it over like this. So now in those 3 or 4 lines, because I have added a line break, we are basically rotating in every direction that is possible. And next we do the following. Let me copy that. Maybe I can also add a comment. So this is the positive rotation, and here we have the negative rotation. So we do the same as before, but now we add a minus sign in front of the rod delta. Like this. Simple, right? And now we do the combinations of that. So how do I call that? Mixing up stuff. No, that's not. I should keep that serious. Let's say combinations. Here, let me quickly sort my thoughts. So this is negative. Okay. Combinations. Positive. That means we are now deleting the minus sign here. And we are adding the rod delta to the next axis here. So we have rod delta 0 in this case. Then we have 0, rod delta. And then we have rod delta 0, rod delta. So these are the combinations for the positive values, for the positive rotation direction. And it's not written that verbose in the original code, so I really need to think about it, trying to explain it and also writing it the correct way. So sorry if this takes a long time, but I really need to concentrate on that. So here we have negative rod delta 0. Then we have 0, negative rod delta. Then we have negative rod delta 0, rod delta. And then this is switched. Oh my gosh. So this is not positive, but this is positive and negative. I have no idea how I can express that more easily, more understandable. But this is positive and negative swapped signs. So that means if we have negative rod delta 0, we now have rod delta, negative rod delta 0. Simple, right? Can you rotate on all 3 axes? I'm dumb, so no, no, you're not dumb. Come on. You made me laugh. About your question, can you rotate on all 3 axes? Yes, I think I can simply change the 0 to also rod delta. The problem with that is that we have the same value for all axes. So this will only work if we play this, if we play around with positive and negative signs. But to really use the whole space of rotations, I would say we would need to have separate values for the rotation delta. So we would need a rod delta x, rod delta y, and rod delta z, and then combine them. And this can get quite complex. There are, of course, ways to do this in nested for loops, but the original code base from the LDSO, which I do not want to say anything negative about, definitely not. It's just doing it this way. So it's just listing manually all kinds of rotations that are interesting, and that's it. It's really, it just looks complicated, but it's really a simple idea. Okay, so let me quickly catch up here. Okay, as I said, we now have rod delta positive, rod delta negative here, 0. Then we have 0, rod delta positive, and rod delta negative. And here we have rod delta positive, 0, and rod delta negative, like this. Okay, and now I think we can add a good comment here. Combinations where we have only negative without swap signs. So that means we start again with here negative rod delta 0. Then we have 0, negative rod delta, so only negatives here. And the last one is negative rod delta, 0, negative rod delta, like this. Okay, now about your question, actually, this is being done here. So we say that we have a rotation around all axes or axes. Let's make it more of a boss. Rotation about all axes. And that is positive and negative this time. So how does that look like? We simply add the negative rod delta to every axis here, and we just switch the signs or swap the signs. So the next line is negative rod delta, and then positive rod delta. Then we have negative rod delta, then we have positive rod delta, and then negative rod delta. So this is all negative, this is negative, negative, positive. This is negative, positive, negative. We have a couple more of them. Negative, positive, negative. Negative, positive, positive this time. Then we have positive, negative, negative. Then we have positive, negative, and positive. And we have positive, positive, negative. Positive, positive, negative. And the last one is all positive. Okay, but now we are finished with this. Yeah. I don't know how to call it. Combination of motion hypotheses. Of course, one can do different combinations. I'm very interested in how they found out that this works. It's probably like trial and error because, I don't know. Can this really be theoretically proven? Yeah. Okay. Next we want to check if not as last pose valid or not as pre-last pose valid or not last f frame pose valid. Then last f2 fh tries clear and last f2 fh tries push back SE3. Okay, so if we do not have valid poses for the second last, second to pre-last, or the last, if those poses are not valid, then we cannot just use the inverses of them and the relative motion and stuff. We just clear all the tries that we have created before, and we simply push back the identity. So we say we are not moving. We are assuming 0 motion. It should be here. Okay. We still need to continue with that because now we have added the initial values, so the initial hypotheses for the poses, and now we need to do something with them. We first create a vec3 of flow vecs, which is equal to vec3 100 100 100. And this, by the way, I think this was the whole funny part about this method. But maybe there's something else funny. That's just something I remembered from my previous research. Now we are talking about the actual creation of the tracked poses. So we are now using the poses, and maybe something else will happen here, which is also quite interesting and funny, but I don't know. So vec3 flow vecs is so far correct. Then we create a SE3 last f to fh is equal to SE3. So this is again 0 motion, and f light f g2l is equal to f light 0, 0. So here we initialize the values for the flow vectors for the last frame to the current frame and for the affine light parameters, which is probably once again here A and B. Question mark because I'm not sure about that. As long as max res for immediate accept is not reached, I'll continue through the options. I'll keep track of the so far best achieved residual for each level in achieved res. So this is probably a pyramid level. And if on course level tracking is worse than achieved res, we will not continue to save time. Okay. So those are important information. This is important information for us on what we want to keep an eye on. And next we will create a 5D vector with the achieved res, which we initialize using vec5 constant with a none, which is, I think, not a number. Then we have a boolean have one good, which is false. And then we have an integer try iterations is equal to 0, and then we start a for loop. In this for loop we have an unsigned int I equals 0, I is less than last f to fh tries dot size, and we increment I. Then we create a new f light f g2l. This is equal to f last to l, and se3 last f to fh. This is equal to last f to fh tries at position I. Okay, so we are basically storing the current try that we have, the number of tries that we have filled up here. We are just iterating through them and storing the current try, this actual try, and the current affine light parameters A and B, which are the same for every iteration. And what do we do now? We use the course tracker to solve the iteration. So we have a bool, tracking is good, is equal to course tracker, and then track newest course, and the parameters are our fh, the frame hashing, the last f to fh, this, and f g2l, this. So we pass the current motion hypothesis and the current affine light and the current frame hashing to this course tracker track newest course and hope that this will succeed. We also need to add that we want to have the pyramid levels used, decremented, -1. And we want to have the result stored in achieved res. And the explanation is, in each level has to be at least as good as the last try. Okay, so probably we can delete this in and say each level has to be at least as good as the last try. Yeah, something like that. And next we increment the try iterations. But that's not everything. So now we have tracked our frame using the course tracker, trying basically to move from the current frame hashing with this motion to the next frame hashing, or maybe it is inverse. Yeah, basically, yeah, I think something like that. Okay, so we need to basically track the images, the current image, based on the hypotheses we have created, and this will return us a bool if the tracking is good or not, and we will get the achieved res, which is probably residual. Achieved res. Yeah, achieved residual, yes. But why is it a 5D vector? This will get clear once we have implemented the course tracker. So currently, unfortunately, it's unclear. But we know that we can use the course tracker to track images. Next we find out if do we have a new winner. So if tracking is good and standard is finite, cast to float, course tracker, last residuals at position 0, and not course tracker, last residuals at position 0, greater or equal to achieved res at position 0. So if this is true, then we want to set the flow vex equal to course tracker last flow indicators. Then we have f g2l is equal to f g2l this, and last f to fh is equal to last f to fh this, and have one good is true. After that, we want to take over achieved res always. So if we have one good, then we loop through with int I equals 0, I is less than 5, and I++. And we check if not standard is finite. Cast to float. Achieved res at position I. Or achieved res at position I is greater than course tracker last residual at position I. Okay, I mixed up something. Okay. This is not at position I. Ah, yes it is. Okay, if not standard is finite. Float. Achieved res at position I. Or achieved res at position I is greater course tracker last residuals at position I. Then achieved res at position I is equal to course tracker last residuals at position I. There is a comment here. Take over if achieved res is either bigger or none. So if it's not finite, then it's none probably. Or if achieved res is bigger than course tracker last residuals at position I. Okay, what I don't like is this I is less than 5. I would like to add this maybe as a to-do for me. Replace 5 with, what are we looping through here? Achieved res. Probably achieved res dot size or something like that. As a question, oh, is it not a VEC 6 because we don't have scale? That's a good question. A VEC 6. Not sure how you mean it. Maybe you can elaborate a bit on that. A VEC 5. Let's see. This is achieved res. Yeah, one would need to know what achieved res actually is. And I can only answer that if I implement the course tracker, and in the course tracker this track newest course, because there we will fill up the achieved res. And to be honest, I'm not sure if the residual will contain the scale, because we cannot observe the scale, in my view. So the residual will probably include like the image intensity, that's one dimension. The other two dimensions will be A and B, so image brightness and contrast. And what are the remaining two? Not sure. Cannot answer this at the moment, I'm sorry. Oh, there was another question. Does this turn out to be better than sampling randomly? I think I missed your question at the correct point. Are you referring to this motion hypothesis, Rahomo, or are you referring to something else? Maybe you can write it again in the chat. Sorry about that. I somehow missed your message. But in general, I would agree. So random sampling is usually always worse than some kind of intelligent sampling. But yeah, sure. Yes, what? Okay, yeah, yeah. The motion hypothesis. I think the way they did it here, they probably have thought about it a little bit. It seems a bit random, to be honest, but I think it is actually a good idea, because I think even in OrbSlam 3 they also use only, I think, constant motion. So there's just a single line, and in the LDSO they at least try to do like double motion, half motion, zero motion, which is probably, I mean, if it does not cost anything to evaluate those hypotheses, then it is probably a good idea to add some more, and then the system, the whole Visual Slam, will probably be more robust. But I'm not certain about that, so I'm just assuming things here. Okay. But thank you very much for the questions. It's really interesting to get those questions and to think about it myself. I like it. Okay. So if we have one good, then we go through the last residuals or achieved residuals and see if we need to update them. After that, we check if we have one good and achieved res at position 0 is less than last course RMSE at position 0 times setting retrack threshold. So this is a setting that can be set in this settings.header file and cc file. This is a custom setting where we can say, okay, I want to have at least an achieved residual at position 0, which is less than the RMSE times this threshold. I will just finish this if statement and I will read your chat message then. And if this is true, then we want to break, because we are fine. Okay, this is interesting to me. I've never worked without an IMU. Ah, okay, I see. So I've never had to think about how to approach this. Yeah, nice. Yeah, true. Definitely. The IMU will help in this a lot, and the IMU will also, I think, give you a hint about the scale. That's why nowadays the fusion of Visual Slam and IMU, so Visual Inertial Slam, is a good idea, I would say. And I'm not sure if the LDSO, if there is a fusion with IMU in the LDSO, but if you could, I mean, you would have to somehow load your IMU data in this main file, pass it onto the full system, and then you can probably just fill up those tries here. I think it's not the best way to do it like that, but you could probably fill up those with your IMU data instead of this, yeah, heuristic or empirical values, and then probably it would also work to have your IMU integrated with that. Is that something you are currently doing your research in, or maybe you can describe that a little bit? I would be very interested to know. I would be very interested to know if this is something you do privately, or if you're working in a company, or are you studying? Yeah, maybe you can tell me that. Would be nice. Okay, so in this case we want to break here because we are finished. But if we do not break, then we want to continue and we want to check if not have one good. In this case we want to log a warning. And we want to say big error. End line, and after big error we write tracking failed entirely. Take predicted pose and hope we may somehow recover. May somehow recover. Yeah. That's a big problem. If we only have the images, we really need to hope for the best. The flow vecs are equal to vec3 0 0 0 and fg2l is equal to f last to l. And last f to fh is equal to last f to fh tries at position 0. Okay, for a company, I have done direct and dense tracking with depth images. I just used the IMU to give me a decent prior. Nice. Cool. Can you say something about in what areas you are using this kind of tracking for direct and dense approaches? So is it in autonomous driving, or is it in, I don't know, maybe even in game design? There are many fields where this can be applied. And thank you, by the way, for engaging. It's really, really interesting this way. Course RMSE. So the last course RMSE is achieved res. So we update that here. And then we set the pose of new frame. We add this check. Course tracker. Last ref. Frame is not equal to null pointer. For quad rotor drones. I think you mentioned it in the beginning. Yeah. Nice. Wish you good luck with that, or big success, I mean. It's really an interesting field, I think. SE3 cam to world is last f frame get pose dot inverse times last f to fh dot inverse fh frame. It is. I love it. Yes, so true. I can totally imagine that you love it. it's nice if someone or if one can really love his or her job. It's that's the way it should be, right? Even though it might be hard from time to time, because many things are not that well explored or like bleeding edge or need to be researched. But this also kind of makes the fascination for me, because it's you can always experiment and always there's something new. The job will never get boring, because there are many problems which are not solved yet, and finding solutions to that, it's yeah, it's really interesting. Okay, what do we do here? We convert from the relative pose to our yeah, absolute pose, our world expressed in world coordinates, pose expressed in world coordinates, and then we set the pose of the current frame hessian. So we basically update our current frame hessian frame object with the pose and with the affine parameters that we have found out here. And I think we are almost finished with that. It is also great because there's a lot of parallelism to exploit. It's all blazing fast on a GPU. Oh yeah. Oh yeah. If you can use all of those calculations, the matrix vector multiplications, for which GPUs are perfect, yeah, if you can really exploit it, if you know how to do that, you can make a really nice and fast system. Sounds interesting. Next we check if course tracker first course RMSE is less than 0. Course tracker first course RMSE is achieved res at index 0. So we also update the course tracker first course RMSE if it's not set yet, so if it's less than 0. There's many things to keep track of. It's really complex. Then we log an info, of course, tracker tracked AB. Here we have this A and B values. Okay, tracked A and B is equal to. Then we add the affine light parameters, G2L dot A. So there's an A field in this data type, it seems. And if there's an A type, there should also be an affine G2L dot B value. Next we have this exposure. Okay, I will change this from exp to exposure. This way I find it more readable. And then we take from FH, we take AB exposure, which we have initialized using the exposure values from the dataset. But they might have been adjusted here in the tracker. So now they are different to what was given in the dataset probably. And now we close the parenthesis and print out res from achieved res at position 0. And then we end the line. What I got now. Good luck with your code. Thank you, and have a great evening or morning, whatever it is for you. For me, it's almost midnight, 7 minutes before midnight. So yeah, see you, goodbye. Thanks for watching. And we finish by returning. Return vec4. Flow vex at position 0. And we have a 3D vector here, so we need that 3 times. Okay, so now at least we know what this vec4 contains. So it contains the achieved residual at position 0. What the other values are, I don't know. I don't know at the moment. And it contains the 3 flow vector values. Would be nice to visualize that at some point. Okay, but so far it's clear. So Rahamo, what is the situation for you? Are you just trying to, or are you just enjoying a Twitch, or what are you doing at the moment? Maybe you can tell me. Okay. Now we have almost finished 1/4 of the whole implementation. And I'm getting a bit tired, to be honest. But I think I will continue with a few methods and then call it a day or a night. So the next method is void FullSystem block until mapping is finished. I'm just sitting here watching and thinking I don't have anything planned for the day. Okay, that's good. So it's a day for you, it looks like. You probably are in the US or I don't know, some other country. Maybe also with a good weather. Okay, block until mapping is, yes, in the US. Okay, nice. Great. I have never been to the US. I want to go there once. It's really a country where I really want to go at some point. Yeah. Okay, here we create a new scope where we define a unique log. Mutex, which we call log, and this will be based on track map sync mutex. And don't forget the semicolon. If not, run mapping. Mapping is already finished. No need to finish again. So we return. Run mapping is false, and tracked frame signal notify all. Next we have the mapping thread, the join. Not sure why they are joining the mapping thread here. It should already be joined. Ah, I see. Okay, they are preparing stuff before, I think, and then they are joining it to run that, and then they need to wait. Okay, and it's blocking. Okay, if setting enable loop closing, loop closing set finish true, and if global map num frames is greater than 4, global map last optimized or no, last optimize all KFs. Last optimize all keyframes. That's a weird name. Okay, optimize all keyframes is probably a function name. And this is the last one. Then it would make sense. Okay, so if we have loop closing enabled, then we want to finish that loop closing. And we want to check if the number of frames in the global map is greater than 4. Ah, okay, and then we want to finish up the optimization of all the keyframes, probably. Things we will find out once we implement that. Okay, here's a large comment. Update world points in case optimization hasn't run with all keyframes. It would maybe be better if the 3D points would always be updated as soon as the poses or depths are updated. No matter if in PGO, post graph optimization probably, or in sliding window BA. Bundle adjustment BA. So Rahomo, what do you think? What is better? Postgraph optimization or Kalman filtering? What is your opinion on that? Of course, that's not a serious question. But maybe you have an opinion on that. Update all world points. Depends, yes. Great answer. On what does it depend? That face, it's really, really funny. Okay, next method, void FullSystem. Make keyframe, shared pointer, frame hashion, FH. But I probably always prefer vector graphs if I have the compute for it. Yeah. I mean, mathematically, I think there is a possibility to always describe your problem using the vector graph formulation. Well, is it like that? And then I think it doesn't matter if you are using postgraph optimization or Kalman filtering. It is described the same way. But maybe I'm opening a can of worms here. But I think I read it somewhere that the vector graphs are basically like the general kind of mathematical formulation for a state estimation problem. Okay, so we have a shared pointer for the frame. Frame is equal to frame hashion, frame. Auto ref frame is equal to frames.back. And we have a scope. Unique. Lock. Mutex. CR lock. Shell. Pose mutex. FH set. Eval PT scaled FH get pose FH frame FG2L FH frame set pose opti with a sim3 FH frame get pose matrix. It's described the same, but the Kalman filter forces you to marginalize everything, so it's less forgiving if you accept a bad measurement. Ah, yeah. At least that's how I think about it. Maybe I'm wrong. Okay. Yeah. Forces you to marginalize everything. I'm not sure about the marginalization, what it means. So, as far as I understand it from the LDSO, marginalization means you have this sliding window, and of course you can implement this sliding window in a Kalman filter as well, not only in your postgraph optimization. And once you are leaving this sliding window, so if we take a look at how this is displayed here in the DSO. So basically the sliding window is depicted on the left hand side, depicted with those keyframes, keyframe 1 on the bottom left, and then keyframe 7 here in the center of the left hand side. And the blue poses in the 3D view, they depict this sliding window. And the marginalization, as far as I understand it, is when frames are leaving this this sliding window. So when you say, but the Kalman filter forces you to marginalize everything. So you are basically, correct me if I'm wrong, you're basically saying that in the Kalman filter you do not have this kind of window, but you have only like the Markov assumption, like Markov chain of first order, where you have only the current state, which is based on all the previous states. So therefore you marginalize everything besides your current time step, or I'm not sure if I understood you here correctly. Okay, next log info. Write the Markov assumption. Yeah. But isn't it possible to extend your Markov chain to incorporate multiple time steps as well? MSCKF is clever about essentially creating a sliding window. Ah, okay, yeah. I've never worked with the MSCKF. What does it stand? Multi-state constraint Kalman filter, I think, but I'm not sure. Interesting. That's right. Okay, interesting. Yeah, for me, it's already difficult to create a motion model in the Kalman filter that takes into account rotations. So in my master thesis and my research, I've only implemented a Kalman filter, like a linear Kalman filter, that only estimate the position when fusing Visual SLAM and GPS, for example. But I was not able to integrate the rotation of the moving platform, or like, I don't know, these formulas. But I just need to take more time to do that. It's not as simple. In the Visual SLAM, I can just write my matrix multiplications, but in the Kalman filter, you need to, of course, you also have matrix vector multiplications, but you need to know the physics behind that, and yeah, that's a bit of a trouble for me. But I'm getting there at some point. Okay, we log that we have the frame, FH frame ID is marked as keyframe, active keyframe. Active keyframes is frames.size. End line. So the active keyframes are stored in the frames data structure. And this means the active keyframes are probably the ones that are used in the sliding window. I'm not sure what active means in this case, but I would assume that. Okay, next we trace new keyframe. That's why we call trace new course. unique lock mutex lock map mutex. Flag frames to be marginalized. And there we have it once again, the marginalization. And here we flag frames for marginalization. FH. Add a new frame to Hessian struct. And also this Hessian here. They call it Hessian in this code. But I think the Hessian, from a mathematics point of view, is something different. I didn't find it yet in the code to find like the real Hessian, like the second derivative, like the Jacobian is the first derivative and the second one is the Hessian. And from this you can somehow calculate the covariance matrix, but this is something I have not found yet in this code. This would be nice to know, for example, if you have a pose, to know what kind of uncertainty this pose has. And this is something which Kalman filtering gives you like out of the box, which is very nice in my view, to have like an uncertainty measure, which you can use for fusion, which is like one of the applications of a Kalman filter. It's not that easy in this, at least from the code that I saw here, it's not that easy to get that. I think the inverse Hessian gives you a lower bound of your covariance, right? Yes. I thought the inverse Hessian gives you the covariance matrix. If it's the lower bound, I'm not sure, but yeah, probably you're right. Never thought about that. You mean like the Kramer-Rao lower bound, or? I need to think about that. It's a good point. Frames mutex. Frames push back. FH frame. FH frame KF ID is equal to FH frame ID is equal to global map num frames. Energy functional insert frame FH H calib MPCH, and then set precalc values. Okay, what do we do here? We flag the frames for marginalization, and then we add a new frame to the Hessian struct. Okay, so the Hessian, okay, maybe it's related to the paper. If we take a look again at the DSO paper, then we have this Hessian here. So we have the poses in the upper left corner. Then we have the pose and geometry or correlation, or yeah, the combination. And then we have the geometric, like the 3D points here. And if we add a new frame here to the poses, maybe we can think of the Hessian. I mean, it's not exactly the matrix in the data structure there, but maybe they mean it like that, the authors. That we can think of that we have like the pose Hessian here, this Hessian part for the poses, which are our frame Hessians. Then we have the geo, like this diagonal here, which is the point Hessian. And then we have the combinations, which are something else, maybe. This is just complex, but still interesting. Okay, so we add a new frame to the Hessian struct and we extend it this way, which is in this case just a simple standard vector, but mathematically it's a matrix. Okay, after we set the precalc values, we add new residuals for old points. Log info, adding new residuals. End line, int num forward res addi is equal to 0 for auto FHT through frames. We say we go through all active frames. Create a new shared pointer of the frame Hessian and create an FA1 is equal to FHT frame Hessian if FH1 is equal to FH, then we continue, and otherwise we make a new for loop with auto feed FHT features. So let's add a comment, go through all, are they active? It's the next step. So let's write an if statement. If field status is equal to feature status valid in capital letters and feed point status is equal to point status active. Okay, and that explains it. So go through all active feature points. Let's move it here. And let's create a new shared pointer with a point hashing. pH is equal to feet point mp pH. Add new residuals into this point hashing. And we have shared pointer point frame residual. We call it R with new point frame residual pH, FH1 and FH. And this is the residual from FH1 to FH. This is the residual from FH1 to FH. What is FH1 again? This is the current frame hashing stored in the frames. And the frames are all active frames. All active frames. Not sure what is done here. As with many things. Shared pointer, point frame residual. Ah, okay, this is probably now, if it really is related to this hashing, then the point frame hashing is probably the green one here. The pose geo part. If I can imagine it like this by using the images, it's always easier for me to have images that depict specific things. Okay, whatever. Let's just hope for the best. Okay, next we have this R residual, which is the point frame residual. And from this we set the state, which is res state in. And we have the pH, the point hashing, I think. Yes, point hashing, residuals dot push back and EF insert residual R. And we have the point hashing last residuals at position 1 is equal to point hashing last residuals at position 0. Then we have point hashing last residuals at position 0 is equal to pair of shared pointer of type point frame residual and res state and we initialize that by using R and res state in. So the residuals also have some kind of state variables. They can be in and they can be something else, which we will find out later. Num fwd res addy plus plus. Maybe it would be smarter to build the full system up in the order of how it is used. Still not sure if this was a really smart idea to start the full system like this. But it is how it is. Okay, next where are we, by the way? What is this? This is the for loop. Okay. After processing all active frames. So here we are basically just changing our residual structure. We are adding our residuals to the hashin. So we are building up the hashin structure, it seems here, by just using those lists. So not mathematically, but from an algorithmic point of view, at least. Next we activate points and flag for marginalization. So activate points empty for multi-threading, and an energy functional make IDX. Next, we optimize, in capital letters, optimize all. That is, we take the frame hashin, we take the frame energy, TH, threshold probably, which is equal to frames.back. And then from the last frame, we take the frame hashin. And from that we take the frame energy, TH. Then we log in info. That we call optimize on keyframe. Then we print out the frame KF ID. End line. And we calculate the RMSE, the root mean squared error. Optimize with setting max opt iterations. And after that we log an info again that we optimize is done. Okay, that's not everything. We have next to figure out if Initialisation failed. So we need to figure out if the initialization has failed. How can we do that? We need to define an integer for the number of keyframes. numkfs is equal to global map and then numFrames. Then we have an if statement where we check numkfs is less than or equal to 4. And here we check if numkfs is equal to 2 and RMSE is greater than 20 times benchmark initializer slack factor. And if this is true, then we log a warning, which reads, I think initializatino failed. Resetting. End line. Then we log an info. RMSE is equal to RMSE end line, and init failed is equal to true. Let's fix this typo. I think initializatino initialization. No, that's wrong. Initialization, like this. Initialization. I think it's correct this way. Okay, we copy that check and repeat it twice. For number of keyframes is equal to 3 and number of keyframes is equal to 4. And we repeat it with benchmark initializer slack factor times 13 and 9 with the same error printing. So it might happen that this, okay, it will not happen that this will be printed 3 times, because num keyframes will always just have one value. Okay, interesting. Why those magic numbers with 20, 13 and 9? Why are there those? Why are there magic numbers? I don't understand it. It really makes things hard to understand. Okay, after that we check if not is lost. No, if is lost. If is lost, then we return. But where do we set that? Nowhere. Oh, interesting. Did I miss something? No. Okay. Maybe it's set. It is set before in another method. So let's continue. Continue with remove outlier. Remove outliers. That's a function we can call, and simple as that. That's everything. And we swap the course tracker for new keyframe. We create a new scope for that and write unique log of type mutex cr log with course tracker swap mutex course tracker for new keyframe, and we make a K, a calibration probably, H calib mpch. Next we have a vector of a type shared pointer, frame Hessian, FHS. Then we loop through for auto and F over frames. And in the body of the for loop we say FHS dot pushback F and then frame Hessian. F frame Hessian. Yes, that's everything. And after the for loop we have a course tracker for new KF. And here we set the course tracking ref of FHS. Like this. Okay, next we activate marginalize points. And here we have traditional bundle adjustment when marging all points. Marginalizing all points. First we flag points for removal. Then we have the energy functional where we drop points F. Then we get the null spaces. Get null spaces, that's a function that we have prepared, and we fill it with energy functional last null spaces pose, comma. We have the pose null space, we have the scale null space, and we have the affine A and affine B parameters, which we all get from our energy functional. Oops. And after that we can call energy functional marginalize points F. Okay, and next we add new imager points and new residuals by calling make new traces with frame Hessian and 0. Next we record the relative poses, and note we are building a co-visibility graph in fact. That's interesting. So there's a co-visibility graph here built. We start with the auto, min and max, which is equal to standard, min max. Oh, cool. Yeah. Yeah, that's definitely cool. I don't know what this will what we need to do for that, but we will find out. Min-max element. Standard min-max element. Frames.begin. Frames.end. And CMP. Frame KF ID. Min-max element based on the frames. And what is CMP frame? Compare frame keyframe ID. That's probably a function which we need to implement at some point. So we take the minimum element and the maximum element. Ah, okay. From all the keyframes, I see. Okay, so we are comparing the keyframe ID, it seems. And based on that, we take the minimum and the maximum. Okay. Now we extract that. So we have an unsigned long min kf ID is equal to the pointer or the dereference operator of min and max dot first. And from that we take the keyframe ID, which is a small d. Keyframe ID. And we do the same for the max. Max keyframe ID, oh, this should be in small letters here. Keyframe ID. Min and max first and min and max second. Okay. This way we have our minimum keyframe ID and the minimum and the maximum keyframe ID. Okay, what do we do now? We check if we have the setting fast loop closing equal to false. Then we record all active keyframes. We loop through all frames, so auto and FR over frames. And in the body we have an auto all KFS is equal to global map get all KFS. So we get all the keyframes. Then we have another loop for auto and F2 over all KFS. And here we check if F2 keyframe ID, KF ID in small letters, then it's bigger or greater than min KF ID, and F2 KF ID is less than max KF ID, and F2 is not equal to FR. Okay, let's see what we are doing here. So we take all the keyframes, we loop through all the frames and all the keyframes, and then we compare the keyframe ID to be greater than the minimum keyframe ID and less than the maximum keyframe ID, and we also want to ensure that the current keyframe is not equal to the frame. Okay. If this is true, then we have a unique log. Unique log of type mutex. Log fr mutex pose rel. Oops. And we have another mutex log2, which is f2 mutex pose rel. And with those locks, we can now change those values of fr pose rel at position f2, which is equal to sim3. So we initialize that pose rel with a sim3 LD group, and this will be an fr get pose times f2 get pose dot inverse as a matrix, and we do the same with f2 pose rel at position fr, but here we get f2 get pose times fr get pose dot inverse, and from that we get the matrix. All right. That is the code for the setting fast loop closing, if this is false. We're basically swapping the fr and f2 get poses. So in fr we are putting the f2 pose. No, it's not like that. In fr we are manipulating the pose rel at position f2, and for f2 we do it vice versa. I still have no idea what this actually means, what we are doing here. So what is this pose rel? I will find out when I implement the frames. I assume it's somehow the relative pose, or it could also be like a relation. Okay, let's continue. So if this setting fast loop closing is not false, but something else, then we want to only record the reference and first frame, and also update the keyframe poses in window, probably in sliding window. Okay, here we create a new scope. Is it similar to that? No, it's not. So here we want to create another unique lock of type mutex, which is called lock, initialized by frame mutex pose rel. Then we have the frame, and from that we have the pose rel again. And now we take the position, or we take it at position ref frame, and initialize with sim3, with the sim3 Lee group again. And here we initialize the sim3 using frame get pose times ref frame get pose dot inverse. Let's double check it. Pose rel sim3 get pose ref frame get pose inverse. Of course, dot matrix again. And then we have auto first frame is equal to frames.front. Then we have frame pose rel first frame sim3 of frame get pose times first frame this time get pose dot inverse and not to forget dot matrix function call. Okay, after that we want to update the poses in window. For auto and fr over frames if fr is equal to frame, then we want to continue, and if not, then we have a for loop. We loop through auto rel over, as the name already suggests, fr pose rel. So this is a list or an array which we loop through, and we create a new auto f2 which is rel.first, and we call fr pose rel at this position f2 and set it equal to sim3 again fr get pose times f2 get pose dot inverse and then dot matrix and semicolon, and that's it. So this is our for loop, which has something to do with the co-visibility graph. So the pose rel is probably not the relative pose, but probably a pose relation, in fact. We can somehow say that we build up a graph where for a specific frame, fr is related to f2 probably. And this relation is explained using a sim3 matrix. So it's even a pose graph and not only a co-visibility graph. Maybe it's a combination. Okay. Now, after we have this scope, so okay, we have checked if we have fast loop closing, then we need to do something different than in the other cases. Okay, so we have built up our graph here, it seems. And after that, we want to do the visualization. We check if we have a viewer. Then we call viewer publish keyframes. And we pass the frames. We say false to something. And very importantly, we pass the camera calibration, calibration, which is mpch. So this is all about visualization, and next we continue with, we are not finished yet. We continue with marginalize frames, marginalize frames. This will be done in a new scope. And we call that a unique, unique lock. Unique lock mutex. Call it LCK of frames mutex. Then we have a for loop, where we loop using an unsigned int. I is equal to 0, I is less than frames.size, and I++. So if frames at position I, from this the frame hashing, and from that, if this is flagged for marginalization, then we first log an info which tells us mark frame, and which one? We go to frames at position I, then we take the ID, and then we end the line. Next we check frames at position I is not equal to course tracker last ref frame, and then we marginalize the frame of frames at position or at index I, and we set I to 0. Okay, so we loop through all the frames, then we check if the frame hashing is flagged for marginalization. If this is the case, and we print something, we check if the current frame is not equal to the last reference frame. I don't know what happens if this evaluates to true. Probably it's an assert or something. And if this is true, then we marginalize the frame. Okay, now after the scope, we continue to add current keyframe into map and detect loops. We do that by calling the global map, and here we had an add keyframe method, which we pass the FH frame object. Then we check if setting enable loop closing is true. Then we also need to call loop closing, this time insert keyframe of the frame. And after we have processed all of that, we can log an info which tells us make keyframe done. Okay, and I think I'm also done for today. This is, I think, the longest stream I have made up until now. But we still have almost 3/4 of the Visual Slam FullSystem.cc still in front of us. So maybe the next stream will be even longer. But for now, I'm getting a headache, so I will stop here. This has been great. Thanks for streaming. Thanks for watching. I can only thank you that you have really stayed until now. If you want, you can of course follow me, and then you will. If you liked it that much, you can of course watch the rest and see if I in 10 years or something finish the LDSO. Yeah, thanks for watching, and it was nice to discuss the details about robotics with you. And yeah, good luck with your work, and see you next time. Goodbye.